Welcome to this gentle exploration of one of the universe's most profound and quiet miracles. Tonight, we drift into the vast, seemingly empty spaces between the stars, where silence reigns supreme, yet where the most extraordinary creative forces are perpetually at work. In these cosmic cathedral halls, where no sound can travel and no wind can blow, gravity performs its ancient alchemy, transforming the ethereal into the eternal, the invisible into the magnificent. There is something almost musical about the way we speak of stellar birth, even though we know that in the vacuum of space, no symphony of sound accompanies these cosmic events. When we say the silent birth of stars, we're acknowledging a beautiful paradox that lies at the heart of astronomy. The greatest creative acts in the universe, the forging of new suns, the construction of planetary systems, the very processes that make life possible, all unfold in perfect, absolute silence. Picture, if you will, drifting through the space between stars on a hypothetical journey that might take millions of years. You would encounter what seems like pure emptiness, a void so complete that it makes the deepest ocean trenches seem crowded by comparison. Yet this apparent nothingness is alive with potential. In every cubic meter of what we call empty space, there are still atoms, hydrogen mostly, the universe's simplest and most abundant element, waiting patiently like seeds scattered across an infinite field. The dance of gravity begins long before we see any visible signs of a star. It starts with whispers, gravitational whispers that are so gentle, so subtle, that they make the lightest touch of a feather seem violent by comparison. Individual atoms, separated by distances that would take light itself considerable time to cross, somehow feel each other across these vast gulfs. They respond to an invitation that has been extended since the universe first cooled enough to allow matter to clump together, roughly 13.8 billion years ago. This gravitational conversation happens on timescales that dwarf human comprehension. While we measure our lives in decades, while civilizations rise and fall over centuries and millennia, gravity works with the patience of eternity itself, the same force that keeps your feet planted on Earth, that holds the moon in its celestial orbit, that binds our solar system together, is also reaching across light years of space, gently encouraging particles of hydrogen to begin the slow dance of aggregation that will, eventually, birth a star. There is something profoundly calming about contemplating this cosmic patience in our hurried world, where we measure success in quarterly reports and satisfaction in instant gratification. The universe reminds us that the most beautiful and lasting creations require time, vast, almost incomprehensible amounts of time. The star that might be born from today's whispered gravitational conversation will take millions of years to form, will burn for billions of years, and will seed the cosmos with heavy elements for trillions of years to come. Yet perhaps the most beautiful aspect of stellar birth is how it connects the smallest to the largest, the most intimate to the most cosmic. Every atom in your body was forged in the nuclear furnace of a star that lived and died long before our solar system was even a gleam in a nebulous eye. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created through the same gentle gravitational processes we're exploring tonight, in stellar workshops that operated on timescales that make human history seem like a brief flicker. When we speak of the silent birth of stars, We're really speaking about gravity's role as the universe's most patient and persistent architect. While we can see the dramatic explosions of supernovas, the brilliant flares of stellar coronas, the spectacular collisions of galaxies, it's easy to forget that all of these cosmic fireworks are built upon foundations laid by gravity's quiet, invisible work. This silence is not empty, but full of potential. It's the silence of the composer before the first note, the silence of the sculptor before the first strike of chisel on stone. In the vast spaces between stars, gravity is composing symphonies of matter that will play for billions of years. It's sculpting the raw material of creation into forms that will nurture worlds, warm planets, and perhaps, in ways we're still discovering, give rise to the very phenomenon of consciousness itself. As we embark together on this gentle journey through the cosmos, we'll discover that what seems like emptiness is actually abundance. What appears to be stillness is actually motion, and what sounds like silence is actually the universe singing itself into ever more complex and beautiful forms. The birth of stars is indeed silent in terms of sound waves, but it resonates with gravitational waves, with electromagnetic radiation, with the deep harmonics of space-time itself. Tonight, somewhere in our galaxy, gravity is gathering the ingredients for tomorrow's stars in molecular clouds so vast they dwarf our entire solar system, in regions so cold they approach absolute zero. The universe is preparing its next masterpiece, and in the perfect silence of space, creation continues its eternal work, one atom at a time, one gravitational whisper at a time, building worlds with a patience that makes mountains seem restless. In the quiet depths of space, where the dramatic electromagnetic storms of stars seem distant and the strong nuclear forces remain locked within atomic nuclei, gravity emerges as both the gentlest and most paradoxical force in nature. It is weaker than the electromagnetic force by a factor of about 10 to the power 36, a number so large that if you wrote it out in standard notation, you would need more digits than there are atoms in a large mountain. Yet this gentle giant shapes the architecture of the entire universe. There is something almost musical about the way gravity works. Unlike the sharp, immediate effects of electromagnetic forces, the spark when you touch a doorknob, the sudden attraction of a magnet to metal, gravity operates more like a slow, deep bass note that resonates through the fabric of space-time itself. It never pushes, only pulls. It never repels, only attracts. It is the universe's way of saying that all matter, no matter how distant, no matter how different, belongs to the same cosmic family. Picture, if you will, a single hydrogen atom floating in the vast darkness between stars. This atom is so small that billions of them could dance on the head of a pin, yet it carries with it an invisible sphere of gravitational influence that extends, technically speaking, to the edge of the observable universe. Every other piece of matter in existence, from the smallest electron to the most massive black hole, feels this atom's gravitational touch, however infinitesimally faint it might be. The mathematics of gravity are elegantly simple in their foundation, yet profound in their implications. Newton gave us the poetry of gravitational attraction in an equation so beautiful that it fits comfortably on a single line. Every particle of matter attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Einstein later showed us that this attraction is really the curvature of space-time itself, like bowling balls, creating dimples in a stretched cosmic trampoline. Yet this gentlest of forces is also the most relentless. While electromagnetic forces can be shielded, you can hide from radio waves with metal mesh. You can block electric fields with conductive barriers. There is no hiding from gravity. It permeates all matter, ignores all barriers, and operates with the patience of eternity. A photon can travel from one side of the galaxy to the other in 100,000 years. But gravity's influence has been connecting these distant regions since the universe first began to cool. In the cosmic construction project of stellar birth, gravity serves as both architect and construction crew. It begins its work in regions where the matter density is so low that each atom might have only a few neighbors within a sphere larger than our entire planetary system. Yet gravity sees potential in this apparent emptiness, like an artist who can envision a sculpture within a block of marble. Gravity perceives the future star hidden within the sparse distribution of gas and dust. The process begins with what scientists call gravitational instability, a moment when the delicate balance between the outward pressure of thermal motion and the inward pull of gravity tips toward collapse. Imagine a vast cloud of gas, perhaps 10 or 20 light years across, floating in the space between stars. For millions of years, this cloud exists in equilibrium, with the random motion of its particles balanced against their mutual gravitational attraction. The temperature is cold, perhaps 10 degrees above absolute zero. But even at these frigid temperatures, thermal motion provides enough energy to resist gravitational collapse. But gravity is patient. It waits for the right moment, the perfect conditions, the cosmic equivalent of a gentle push. When that moment comes, perhaps from the shock wave of a distant exploding star or the gravitational influence of a passing stellar nursery, gravity seizes its opportunity. What follows is a process so gradual, so gentle, that it makes the growth of mountains seem rapid by comparison. As the cloud begins to contract under its own gravitational influence, something beautiful happens. The very act of contraction increases the density, which strengthens the gravitational pull, which accelerates the contraction, which increases the density further. It's a feedback loop of cosmic creation, as inevitable as water flowing downhill, yet as remarkable as the emergence of life itself. This is where gravity reveals its true power. Despite being the weakest of the fundamental forces, it is the only force that grows stronger as matter accumulates. Unlike electromagnetic forces, which can cancel each other out when positive and negative charges meet, gravity is always additive. Every atom that joins the growing condensation makes the gravitational field stronger, attracting more atoms, creating an ever-deepening well in the fabric of space-time. The paradox of gravity becomes even more apparent when we consider the scales involved. A forming star might begin as a cloud containing the mass of 1,000 suns, spread across a volume larger than our entire solar system. The average density is so low that it makes the best vacuum we can create on Earth seem dense by comparison. Yet gravity, working across these vast distances with forces so small they would be imperceptible on human scales, manages to gather all of this material into a sphere small enough that light can cross it in a few seconds. It is both humbling and beautiful that this same force, gravity, connects the formation of stars to the formation of planets, to the evolution of galaxies, to the structure of the universe itself. The gravity that will eventually create a new star system is the same gravity that holds you to the Earth, that keeps the moon in its orbit, that maintains the delicate dance of our solar system. It is the cosmic thread that weaves together all matter, all energy, all structure in the universe. Meanwhile, across the vast expanse of space, countless other gravitational conversations are taking place in other molecular clouds. Other future stars are beginning their slow journey toward ignition. In some regions, gravity is gathering the ingredients for massive, brilliant stars that will burn fast and die young in spectacular supernovas. In others, it is carefully assembling the components of small, red dwarf stars that will burn steadily for trillions of years, long after our own sun has exhausted its fuel. And in this grand gravitational symphony, there is something profoundly calming about understanding our place. We are not separate from this cosmic construction project. We are part of it. The gravity that shapes stars is the same gravity that shapes our bodies, our planet, our solar system. We are participants in the universe's greatest architectural project, temporary arrangements of stardust held together by the gentlest and most persistent force in nature. In the quiet depths of interstellar space, floating like cosmic islands in an ocean of near vacuum, exist some of the most remarkable structures in the universe. Molecular clouds, these vast, ethereal congregations of gas and dust, are the stellar nurseries where gravity will perform its most delicate and patient work, transforming the tenuous into the magnificent, the cold and dark into the brilliant and life-giving. Picture, if you will, a region of space so large that light itself would take 50 years to cross from one side to the other. Within this volume, matter exists in concentrations so sparse that the best vacuum chambers on Earth seem dense by comparison. Yet this apparent emptiness contains enough raw material to construct hundreds, perhaps thousands of stars, along with their attending families of planets, asteroids, and comets. These are the molecular clouds, nature's most expansive construction sites, where the universe stores the ingredients for its next generation of stellar children. There is something almost dreamlike about the conditions inside these cosmic nurseries. The temperature hovers at roughly 10 degrees above absolute zero, so cold that the very concept of warmth becomes abstract. At these temperatures, most of the universe's elements have condensed into solid grains of dust, creating tiny cosmic snowflakes that drift through the darkness like an infinite, slow-motion blizzard. Hydrogen, the universe's most abundant element, has paired up into molecules, creating H2, the building blocks of future stellar cores. The silence within these clouds is more profound than any silence experienced on Earth. Sound waves cannot propagate in such tenuous matter, and the distance between individual particles is so vast that collisions are rare events, measured in thousands of years. Yet this silence is not empty. It resonates with the subtle gravitational harmonics that will eventually orchestrate the birth of new stars. It is the silence of potential, the quietude of creation, gathering its forces. Within these molecular clouds, matter exists in a delicate balance that has persisted for millions of years. The outward pressure created by the thermal motion of particles, even at these frigid temperatures, exactly balances the inward pull of gravity. It's a cosmic standoff, with entropy and thermodynamics on one side and gravity's patient persistence on the other. This equilibrium is so precise, so finely tuned, that it can persist for tens of millions of years, with the cloud neither expanding nor contracting, but simply floating in space like a vast, dormant seed. The composition of these stellar nurseries reads like a cosmic inventory of creation's raw materials. Roughly 70% is hydrogen, the universe's primordial element, forged in the first few minutes after the Big Bang. About 28% is helium, also a relic of those earliest cosmic moments. The remaining 2% consists of what astronomers poetically call metals, all the heavier elements from lithium to uranium, forged in the nuclear furnaces of previous generations of stars and scattered into space when those ancient suns reach the end of their lives. It's this 2% that makes all the difference. These heavier elements, though sparse, serve as the cosmic equivalent of condensation nuclei in Earth's atmosphere. Just as water vapor needs tiny particles of dust or salt to form raindrops, the gases in molecular clouds need these metallic particles to begin the process of aggregation. Carbon atoms link together into long chains, creating some of the same organic molecules we find in living organisms. Silicon and oxygen combine to form tiny grains of cosmic glass. Iron condensates into microscopic particles that give some regions of molecular clouds their distinctive reddish hue. These dust grains, though individually smaller than smoke particles, play a crucial role in preparing the stage for stellar birth. They serve as meeting places where hydrogen atoms can combine into molecules, and they act as tiny shields that protect the cloud's interior from the harsh radiation of nearby stars. Without these cosmic dust motes, the process of star formation would be far more difficult, perhaps impossible. The structure within molecular clouds is far from uniform. Like weather systems in Earth's atmosphere, these clouds have currents, eddies, and regions of higher and lower density. Some areas are so tenuous that they barely qualify as matter at all, while others have begun to show the first signs of gravitational concentration. These denser regions, called clumps and cores, are where the drama of stellar birth will eventually unfold. As we drift through this cosmic nursery in our imagination, we might encounter regions where the density has increased by a factor of 10 or 100 above the cloud average. These areas, still incredibly sparse by terrestrial standards, represent gravity's first successful attempts at gathering matter. They are the cosmic equivalent of gentle whirlpools in a vast, slow-moving river, areas where the current has begun to circle back on itself, creating the potential for further concentration. Temperature variations also paint intricate patterns across these clouds. While most regions hover around 10 degrees above absolute zero, some areas are even colder, chilled by their own expansion or by the shielding effect of dust. Other regions show slightly higher temperatures, warmed by cosmic rays or by the distant radiation of stars. These temperature differences, tiny as they are, create pressure gradients that can enhance or inhibit the gravitational gathering of matter. The chemistry happening within molecular clouds is surprisingly rich and complex. In the frigid darkness, chemical reactions proceed with leisurely patience, creating an astounding variety of molecules. Astronomers have detected over 200 different molecular species in these clouds, including water, ammonia, methanol, and even complex organic compounds like amino acids, the building blocks of proteins. It's as if these stellar nurseries are also cosmic chemistry labs, experimenting with the molecular combinations that might someday contribute to the emergence of life. Perhaps the most beautiful aspect of molecular clouds is their transient nature. Despite their vast size and apparent permanence, these structures are temporary arrangements, cosmic seasons in the galaxy's long year. Some clouds persist for tens of millions of years before gravitational instabilities or external influences trigger their collapse into new star systems. Others are disrupted by the radiation and stellar winds of the very stars they help create, their remaining material scattered back into the interstellar medium to be recycled into future generations of stellar nurseries. Within the molecular cloud we're exploring tonight, gravity is already at work, though its effects are so subtle that they would be invisible to any observer. Individual particles are beginning to respond to the collective gravitational field of their neighbors, creating microscopic currents in the cosmic gas. These currents, flowing at speeds measured in centimeters per second, represent the first stirrings of what will become a stellar birth. It is both humbling and beautiful that these vast, cold, seemingly empty regions contain within them the potential for such magnificent creation. In the perfect silence of a molecular cloud, surrounded by darkness so complete that it makes the deepest ocean trenches seem bright, gravity is preparing to perform one of its most remarkable feats, the transformation of the ethereal into the eternal, the construction of nuclear furnaces that will burn for billions of years, warming worlds, and perhaps nurturing life across vast expanses of space and time. In the vast, patient silence of a molecular cloud, where equilibrium has reigned for millions of years, there comes a moment of profound change, a cosmic stirring that will transform dormant potential into active creation. This is the moment of disturbance, when external forces gently nudge the delicate balance between gravity and thermal pressure, setting in motion a cascade of events that will culminate in the birth of new stars and the construction of new worlds. There is something almost musical about the way these disturbances propagate through the tenuous matter of a molecular cloud, like ripples spreading across the surface of a cosmic pond. Shock waves and gravitational influences travel through the sparse gas at speeds that seem leisurely by the standards of light, yet represent tremendous forces by the standards of interstellar matter. These disturbances don't arrive with drama or fanfare. They whisper their way through the cloud, creating subtle changes in density and motion that will compound over time into something magnificent. Picture, if you will, the moment when a massive star, perhaps hundreds of light years away, reaches the end of its nuclear lifetime and explodes in a supernova. This stellar death, violent beyond human comprehension, sends a shock wave racing outward through space at thousands of kilometers per second. To any observers in its immediate vicinity, this would be a catastrophic event, capable of sterilizing planetary systems and disrupting the fabric of local space-time. But by the time this shock wave reaches our peaceful, molecular cloud, millions of years later, it has become something gentler, a cosmic breeze carrying just enough energy to disturb the ancient equilibrium. The shock wave doesn't arrive all at once. Instead, it sweeps across the cloud like a slow-motion tsunami, taking thousands of years to fully traverse the nursery's vast expanse. As it passes through each region, it compresses the gas slightly, increasing the density and creating conditions where gravity can finally gain the upper hand over thermal pressure. It's as if the universe has given gravity a gentle push, the cosmic equivalent of helping a shy dancer take the first step onto the floor. Yet supernovas are not the only gardeners in this cosmic nursery. Sometimes the disturbance comes from gravitational interactions on an even grander scale. When galaxies pass close to each other, events that unfold over hundreds of millions of years, their gravitational fields can compress molecular clouds in their spiral arms, triggering waves of star formation that propagate like cosmic dominoes. The Milky Way itself may carry the gravitational memories of ancient galactic encounters, written in the patterns of stellar birth across its disk. Even more subtly, the simple rotation of our galaxy creates its own rhythm of disturbance. As molecular clouds orbit the galactic center, they pass through the spiral arms where matter is more densely concentrated. This passage, which occurs roughly every 100 million years, subjects the clouds to increased gravitational forces and turbulence. It's a cosmic seasonal cycle where stellar nurseries experience their own version of spring, periods when conditions become favorable for new growth and creation. Within our imagined molecular cloud, the arrival of disturbance creates a fascinating chain reaction. The initial compression increases the gas density, which strengthens the gravitational field, which attracts more matter, which increases the density further. But this isn't a runaway process. Not yet. The cloud's response is measured, almost thoughtful, as if it's testing whether conditions are truly right for the enormous commitment of stellar birth. Temperature plays a crucial role in this delicate moment. If the disturbance comes too quickly or too violently, it can heat the gas, strengthening thermal pressure and potentially disrupting the formation process entirely. But when the disturbance arrives, with the right combination of strength and gentleness, enough to trigger gravitational collapse, but not enough to overwhelm it with heat, conditions become perfect for stellar birth. The dust grains scattered throughout the cloud serve as crucial mediators in this process. As the gas compresses and heats up, these tiny particles absorb the thermal energy and radiate it away into space at longer infrared wavelengths. This cosmic cooling system allows the cloud to collapse while staying cold, maintaining the conditions necessary for gravity to continue its patient work of aggregation. As the disturbance propagates through different regions of the cloud, it creates a complex pattern of compression and rarefaction. Some areas experience strong compression and begin collapsing immediately. Others are stretched and expanded, becoming even more tenuous than before. Still others find themselves caught between competing influences, creating turbulent eddies where matter swirls in complex patterns that will eventually settle into the ordered rotation of future star systems. The timing of these disturbances follows no human schedule, no terrestrial calendar. A molecular cloud might wait 50 million years between significant disturbances, maintaining its patient equilibrium while the galaxy slowly rotates around it. Then, within a span of just a few million years, it might experience multiple triggers: a nearby supernova, a passage through a spiral arm, the gravitational influence of a forming stellar association, creating a burst of star formation that will light up entire regions of space. It's during these moments of cosmic springtime that molecular clouds reveal their true potential. What seemed like empty space becomes alive with activity as gravity finally gains the upper hand over thermal pressure. The cloud begins to fragment into smaller, denser regions, each destined to become the birthplace of a star or star system. The process is remarkably efficient. Once triggered, gravitational collapse proceeds with inexorable logic, transforming the ethereal into the concrete over timescales that span millions of years. Perhaps the most beautiful aspect of these cosmic disturbances is their interconnectedness. The supernova that triggers star formation in one molecular cloud was itself born from an earlier episode of stellar birth, likely triggered by disturbances from even earlier generations of stars. It's a cosmic relay race of creation, where each generation of stars passes the torch to the next through their dramatic deaths, ensuring that the universe continues to create new sources of light and energy. Meanwhile, across the vast expanse of our galaxy, similar dramas are unfolding in countless other molecular clouds. Some are experiencing their first disturbances, beginning their transformation from dormant nurseries into active star-forming regions. Others are in the midst of their creative phase, with new stars already beginning to form in their densest regions. Still others have completed their cycle, their matter scattered and recycled into the interstellar medium, ready to be incorporated into future generations of stellar nurseries. And in this grand cosmic rhythm of disturbance and creation, there is something profoundly calming about understanding our own connection to these processes. The disturbances that trigger star formation are the same forces that shaped our own solar system billions of years ago. The shock waves, gravitational influences, and chemical processes we observe in distant molecular clouds are echoes of the events that created the sun, the earth, and ultimately the conditions that allow us to exist and contemplate our place in this magnificent cosmic dance. As our molecular cloud responds to its moment of disturbance, gravity prepares to begin its most patient and remarkable work, the construction of new stars, new worlds, and new possibilities for the continuation of the universe's greatest story, the ongoing creation of complexity, beauty, and perhaps consciousness itself. In the early years of the 20th century, while Einstein was revolutionizing our understanding of space and time, and while astronomers were just beginning to realize that the Milky Way was but one galaxy among countless others, a British physicist named Sir James Jeans was quietly solving one of the universe's most fundamental puzzles, working in the comfortable libraries and lecture halls of Cambridge University, far from the cosmic laboratories where his theories would eventually be tested. Jeans was discovering the mathematical poetry that governs when and how gravity can transform a wisp of gas into a blazing star. There is something almost musical about the way Jeans approached this problem. He didn't begin with telescopes or observations, but with the elegant language of mathematics, differential equations that could describe the delicate balance between the forces that hold matter apart and the forces that draw it together, like a composer working out the harmonic relationships that make a melody beautiful. Jeans was discovering the cosmic harmonics that determine when a cloud of gas can begin its transformation into something magnificent. Picture, if you will, the challenge that Jeans set himself. Throughout the universe, vast clouds of gas float in apparent equilibrium, some for millions of years, neither expanding nor contracting, but simply existing in a state of cosmic suspension. Yet occasionally, without any obvious external trigger, some of these clouds begin to collapse under their own gravity, eventually giving birth to new stars. What makes the difference? What determines whether a cloud will remain forever dormant or will awaken to begin the long journey towards stellar birth? The answer, Jeans discovered, lies in a critical relationship between mass, temperature, and density, a cosmic equation that determines the fate of every wisp of matter in the universe. When a cloud of gas contains more than a certain critical mass, now known as the Jeans mass, gravity becomes stronger than the thermal pressure trying to keep the gas particles apart. It's a tipping point, a cosmic threshold where the gentle force of gravity finally gains the upper hand and begins its patient work of construction. The mathematics of this discovery are elegantly simple, yet profound in their implications. The Jeans mass depends on the temperature of the gas and its density, following a relationship that reveals something beautiful about the universe's architecture. For a cloud at the frigid temperatures typical of interstellar space, around 10 degrees above absolute zero, the critical mass is roughly equivalent to a few hundred times the mass of our Sun. Any cloud containing more matter than this threshold becomes gravitationally unstable, meaning that even the smallest disturbance will trigger its collapse. But the beauty of Jeans' insight goes deeper than this simple mass threshold. His equations revealed that as a cloud begins to collapse and its density increases, the Jeans' mass actually decreases, making the cloud even more unstable. It's a cosmic feedback loop that ensures, once begun, the collapse will continue with inexorable logic. Gravity, having gained the upper hand, strengthens its grip with every passing moment. Yet this is not a violent or chaotic process. The timescale for gravitational collapse, also derived from Jeans' equations, unfolds with the patience of geology. For a typical molecular cloud, the time required for significant contraction is measured in millions of years, a pace so leisurely that entire civilizations could rise and fall while barely perceptible changes occur in the cloud structure. It's as if the universe has chosen to create its most magnificent structures with the same unhurried deliberation that shapes mountains or carves canyons. The concept of gravitational instability also illuminated something profound about the cosmic inventory of matter. Not all regions of space are created equal when it comes to star formation potential. Dense molecular clouds, with their higher concentrations of gas and dust, have lower Jeans masses and are therefore more likely to collapse into stars. Sparse regions of intergalactic space, despite containing vast amounts of matter when considered in total, lack the density necessary to trigger stellar birth. As Jeans developed his theory further, he discovered that the process of collapse doesn't happen uniformly throughout a cloud. Instead, the regions with the highest density, those that exceed the local Jeans mass by the greatest margin, will collapse fastest, creating a hierarchy of structure formation. This insight would later prove crucial to understanding how individual clouds can fragment into multiple star-forming cores, each following its own gravitational timeline. The temperature dependence of the Jeans mass revealed another layer of cosmic poetry. Hot gas, with its vigorous thermal motion, requires a much larger mass to become gravitationally unstable than cold gas. This means that the universe's stellar nurseries are preferentially located in its coldest regions, the dark, frigid molecular clouds, where temperatures hover just above absolute zero. It's a cosmic irony that the birthplaces of the universe's hottest objects are also its coldest regions. Modern astronomers have refined and extended Jean's original insights, incorporating the effects of magnetic fields, turbulence, and rotation that he couldn't have anticipated in 1902. Yet the fundamental principle he discovered remains unchanged. There is a critical threshold, a cosmic point of no return, where gravity transitions from being a passive influence to becoming an active architect of stellar creation. In today's observatories, astronomers can actually observe the gene's instability in action. Using radio telescopes that can peer through the dust-laden molecular clouds, they map regions where the density exceeds the local gene's mass and predict where new stars will form. These observations confirm Jean's century-old calculations with remarkable precision, showing that his mathematical poetry accurately captured something fundamental about the universe's creative processes. Perhaps the most beautiful aspect of Jean's discovery is how it connects the largest structures in the universe to the smallest. The same physics that determines when a molecular cloud will collapse into stars also governs when the universe's first overdense regions collapsed to form galaxies. When those galaxies began forming their first stellar populations, and when our own solar nebula contracted to form the sun and planets, the gene's mass is a universal principle, operating on scales from stellar systems to galactic clusters. As we contemplate the molecular cloud in our cosmic journey, we can imagine it poised at this critical threshold, perhaps triggered by the gentle disturbance of a distant supernova shock wave, perhaps simply through the gradual accumulation of matter over millions of years. Regions within the cloud have begun to exceed their local gene's masses. The die is cast, the cosmic threshold has been crossed, and gravity begins its slow, inexorable work of transformation. It is both humbling and beautiful that this fundamental transition from dormant matter to active stellar birth can be described by equations elegant enough to fit on a single page, yet profound enough to govern the creation of every star in the observable universe. In the mathematics of Jean's instability, we see reflected the deeper truth that the universe operates according to principles that are both comprehensible to human reason and magnificent in their scope and consequences. Tonight, somewhere in our galaxy, a molecular cloud is crossing its gene's threshold for the first time, beginning a journey that will culminate in the birth of new stars, new planetary systems, and new possibilities for the continuation of cosmic evolution. And in that moment of transition, Sir James Jean's century-old insight continues to illuminate the mathematical poetry underlying one of the universe's most beautiful creative processes. Once the cosmic threshold has been crossed, and a molecular cloud region exceeds its critical gene's mass, what follows is perhaps the most patient and majestic process in the universe: gravitational collapse. This is creation in slow motion, a symphony of matter and energy that unfolds over timescales so vast they dwarf the entire history of human civilization. To witness the birth of a star is to observe the universe composing one of its most enduring masterpieces, note by careful note, across millions of years. In the quiet depths of our collapsing cloud core, time takes on an entirely different meaning. While light can race from one side of the forming system to the other in mere hours, the matter itself responds to gravity's invitation with geological patience. Individual gas particles, nudged by the infinitesimal but persistent force of gravity, begin their inward journey at speeds measured in centimeters per second, slower than a leisurely walk, yet as inevitable as the turning of the cosmic seasons. There is something almost meditative about contemplating the early stages of this collapse. Picture, if you will, a region of space, perhaps a light year across, containing gas so sparse that its density is still 1,000,000 times lower than the best vacuum we can create on Earth. Yet within this apparent emptiness, every atom is now participating in a coordinated dance of convergence, responding to the collective gravitational field of its trillion companions. The mathematics that govern this collapse reveal a beautiful relationship between space and time. As the core contracts, its density increases not linearly, but exponentially. A small change in radius corresponds to a dramatic change in the concentration of matter. This relationship, first worked out by theoretical astrophysicists in the mid-20th century, shows that the early stages of collapse proceed with a dreamlike slowness, but the final phases accelerate dramatically as the densities approach those found inside stars. During the first 1,000,000 years of collapse, changes are so subtle they would be virtually undetectable. Even with our most sensitive instruments, the cloud core shrinks from perhaps a light year across to half a light year, while its central density increases by a factor of perhaps 10. These are cosmic baby steps, changes so gradual that they unfold on timescales longer than the entire existence of our species. It's as if the universe insists that its most important creative acts be performed with the utmost deliberation and care. Yet even in these earliest stages, the collapsing core begins to develop structure and character. The center, where gravity's pull is strongest, contracts faster than the outer regions, creating the first hint of the density gradient that will eventually become a star. Temperature variations appear as different regions of the cloud respond to compression at different rates. The initially spherical cloud begins to show the subtle flattening that will eventually become a disk, as any small amount of initial rotation is amplified by the conservation of angular momentum. As the collapse progresses into its second 1,000,000 years, the pace of change begins to accelerate noticeably. The core has now contracted to perhaps 1/10 of a light year across, still vast by planetary standards, but beginning to approach the scale of our solar system. The central density has increased by factors of hundreds or thousands, though it still remains far below what we would consider substantial by terrestrial standards. This is when the first signs of internal structure begin to emerge more clearly. The collapsing core starts to develop what astronomers call a density profile, a mathematical description of how the concentration of matter varies from the center to the edge. The very center becomes increasingly dense, while the outer regions lag behind, creating concentric shells of different density that will play crucial roles in the star formation process. Temperature patterns also begin to emerge during this phase. As the gas compresses It heats up according to the fundamental laws of thermodynamics, but this heating is not uniform throughout the core. The center, experiencing the strongest compression, begins to warm more rapidly than the outer regions. Meanwhile, the cosmic dust grains distributed throughout the cloud act as a cooling system, absorbing heat energy and radiating it away into space at infrared wavelengths. The interplay between heating and cooling creates a complex thermal structure within the collapsing core. Some regions become warm enough that hydrogen molecules begin to dissociate back into individual atoms, absorbing energy and actually cooling the gas. Other regions remain so cold that hydrogen stays frozen onto the surfaces of dust grains, creating a kind of cosmic ice that will play important roles in the later stages of stellar birth. As the third million years of collapse begins, the core has contracted to dimensions comparable to our outer solar system, perhaps a tenth the distance from the Sun to Earth. At this scale, the effects of rotation become increasingly important. Any initial spin of the cloud, no matter how slight, is amplified as the core contracts, just as an ice skater spins faster when pulling in her arms. This enhanced rotation begins to flatten the core into the disc-like structure that will eventually become the birthplace of planets. The central regions of the core have now reached densities where individual gas particles collide with each other, frequently enough to establish what physicists call thermodynamic equilibrium. This marks an important transition in the collapse process from a phase dominated by gravitational dynamics to one where thermal physics begins to play an increasingly important role. By the end of the collapse phase, after perhaps 5 to 10 million years of patient contraction, the core has transformed from a wispy, light-year-spanning cloud into a dense, hot object only about the size of our solar system. The central density has increased by factors of billions, approaching the point where nuclear reactions might begin to occur. The temperature at the center has risen from near absolute zero to thousands of degrees, hot enough to ionize hydrogen and create the first signs of the plasma that will eventually fuel stellar nuclear fusion. Yet even at this advanced stage, the collapsing core is still not quite a star. It's what astronomers call a protostar, a stellar embryo that has developed most of the characteristics it will need for its eventual nuclear awakening, but hasn't yet achieved the extreme conditions necessary to sustain fusion reactions. The protostar glows with thermal energy from its gravitational collapse, but it has not yet learned to generate its own nuclear light. Throughout this entire process, spanning millions of years, and involving the coordinated motion of more atoms than there are stars in the observable universe, gravity has worked with the patience of eternity itself. It has transformed the ethereal into the nearly concrete, the cold and dark into the warm and glowing, the dispersed into the concentrated. It has composed a symphony of creation that will soon reach its crescendo with the ignition of nuclear fusion and the birth of a true star. It is both humbling and beautiful that this most fundamental of cosmic processes, the transformation of gas into stars, unfolds with such magnificent patience. In our age of instant communication and rapid change, the universe reminds us that the most enduring and significant transformations require time, deliberation, and the kind of persistence that only cosmic forces can maintain. As gravitational collapse transforms a molecular cloud from a wispy, ethereal structure into something more concentrated and dense. A remarkable phenomenon begins to unfold: fragmentation. What started as a single, unified region of space begins to divide itself into multiple centers of collapse, each destined to become a separate star. It's as if the universe has decided that stellar birth should rarely be a solitary affair, but rather a communal celebration of creation where multiple siblings are born from the same cosmic womb. There is something almost organic about the way fragmentation occurs, reminiscent of the way a single fertilized cell divides to create a complex multicellular organism. The process begins when different regions within the collapsing cloud reach their own individual genes masses at slightly different times. As we learned from Sir James Jean's insights, any region that exceeds this critical threshold becomes gravitationally unstable and begins to collapse on its own timeline, independent of its neighbors. Picture, if you will, our molecular cloud during its early stages of collapse. What initially appeared to be a uniform region of space slowly reveals itself to have subtle variations in density, temperature, and composition. These variations, perhaps caused by turbulent motions in the original cloud or by uneven heating from nearby stars, create a complex landscape of gravitational potential. Some regions are slightly denser than others, some slightly warmer, some enriched with different concentrations of cosmic dust. As the overall cloud contracts under its collective gravitational influence, these small initial differences become amplified through a process that physicists call gravitational amplification. A region that starts out just 10% denser than its surroundings will become 20% denser as the cloud contracts, then 40% denser, then 80% denser, growing in relative concentration until it becomes a distinct gravitational entity capable of collapsing independently from the surrounding material. The mathematics of fragmentation reveal a beautiful hierarchical structure that emerges naturally from the physics of gravitational collapse. Large molecular clouds first break into smaller clumps, each containing enough material to form dozens or hundreds of stars. These clumps then fragment further into cores, each destined to form a single star or small multiple star system. Finally, some cores fragment one more time into the smallest units, individual stellar embryos that will become the stars we eventually observe shining in the night sky. This hierarchical fragmentation creates what astronomers call a stellar association or star cluster, a family of stars born from the same original molecular cloud, sharing similar ages, compositions, and initial motions through space. The most massive fragments, containing the most material, will collapse fastest and form the largest, most luminous stars. The smaller fragments will take longer to collapse and will eventually become smaller, dimmer stars that may burn quietly for trillions of years. The process of fragmentation is influenced by several cosmic factors that work together to determine the final stellar census. Temperature plays a crucial role. Warmer regions require more mass to become gravitationally unstable, leading to the formation of more massive stars. Cooler regions can fragment into smaller pieces, creating lower mass stars. The presence of magnetic fields, threading through the molecular cloud like invisible cosmic highways, can either enhance or inhibit fragmentation, depending on their strength and orientation. turbulence within the molecular cloud adds another layer of complexity to the fragmentation process. The original cloud contains currents and eddies of gas motion, cosmic weather patterns that create regions of compression and rarefaction. Where these turbulent motions compress the gas, fragmentation is enhanced, creating more numerous stellar embryos. Where turbulence creates expansion, fragmentation is inhibited, leading to larger, more massive cores. As each fragment begins its own independent collapse, it develops its own unique characteristics and evolutionary timeline. The most massive cores, containing tens or hundreds of times the mass of our Sun, will collapse rapidly and form massive, brilliant stars that will burn through their nuclear fuel in just a few million years. These stellar giants will dominate their local environment with intense radiation and powerful stellar winds, influencing the formation and evolution of their smaller siblings. Meanwhile, the smaller fragments, those containing only a fraction of our Sun's mass, will collapse much more slowly and eventually form the red dwarf stars that will comprise the majority of the stellar population. These diminutive suns will burn so efficiently that they can maintain nuclear fusion for hundreds of billions of years, long after their massive siblings have exhausted their fuel and ended their lives in spectacular explosions. The spatial distribution of these fragmenting cores reveals another beautiful aspect of stellar birth. Rather than being randomly scattered throughout the original cloud, the stellar embryos tend to form in groups and associations that reflect the structure of the parent molecular cloud. We observe stellar nurseries where dozens of stars are born in close proximity, creating dense stellar neighborhoods where gravitational interactions will play important roles in shaping the final orbital characteristics of planetary systems. Some fragments develop especially interesting characteristics during the fragmentation process. Binary and multiple star systems, where two or more stars orbit around their common center of mass, are thought to form when a single core fragments at the very latest stages of collapse, creating stellar siblings that remain gravitationally bound to each other throughout their lives. These binary systems are remarkably common, with roughly half of all stars existing as members of multiple star families. The fragmentation process also determines the efficiency of star formation within molecular clouds. Not all of the original cloud material ends up incorporated into stars. Much of it is either blown away by the radiation and stellar winds of the newly formed stars, or remains as a reservoir of gas and dust that may participate in future episodes of star formation. Typically, only about 1% to 10% of a molecular cloud's mass is converted into stars during any single fragmentation event. As we observe the fragmentation process in our imagined molecular cloud, we witness the universe exercising its preference for diversity over uniformity. Rather than creating a single, massive object, gravity has chosen to divide the available material into numerous smaller portions, each destined to follow its own unique evolutionary path. Some will become massive, short-lived stars that will enrich the interstellar medium with heavy elements when they explode as supernovas. Others will become long-lived, stable stars that may nurture planetary systems for billions of years. The timing of fragmentation events across the cloud creates a complex stellar nursery where stars of different masses and ages coexist in the same region of space. The most massive stars, forming first and evolving quickly, will begin to influence their environment while their smaller siblings are still in the process of formation. This creates a dynamic, evolving stellar ecosystem where older stars help to shape the birth conditions of younger ones. Perhaps the most beautiful aspect of fragmentation is how it demonstrates the universe's tendency toward complexity and organization. What begins as an apparently simple cloud of gas and dust reveals itself to contain the seeds of intricate stellar systems, planetary families, and perhaps even the complex chemistry that makes life possible. Through the patient work of gravity and the complex physics of collapse and fragmentation, the universe transforms the simple into the sophisticated, the uniform into the diverse. In the cosmic nursery, we're exploring fragmentation has created the foundation for what will become a rich, stellar neighborhood, a community of stars that will share the same region of the galaxy for millions or billions of years, their fates intertwined by their common birth from the same molecular cloud. Each fragment now begins its own journey towards stellar ignition, carrying within it the potential to become a sun that might one day warm worlds and nurture the emergence of complexity, beauty, and perhaps consciousness itself. As each fragment of the molecular cloud settles into its own gravitational collapse, a profound transformation begins to occur within the deepest regions of these stellar embryos. For millions of years, matter has been contracting slowly and patiently under gravity's gentle but persistent influence. Now, as densities reach unprecedented levels and volumes shrink to solar system-sized scales, the fundamental physics of the collapse begins to change. Temperature and pressure, which have played supporting roles in the cosmic drama up to this point, now step forward as the primary actors in what will become the most crucial phase of stellar birth. There is something almost alchemical about the transformation that begins to occur within the collapsing cores. Matter that has existed in the cold darkness of space for millions of years, at temperatures barely above absolute zero, suddenly finds itself being compressed and heated to conditions that haven't existed since the early moments of the universe itself. It's as if gravity, having gathered the raw ingredients for stellar creation, now begins the delicate process of cooking them into something entirely new. Picture, if you will, the center of our collapsing stellar embryo as it approaches this critical phase. The core, now perhaps only a few times larger than our solar system, contains matter compressed to densities approaching those found in terrestrial materials. Individual atoms, which have been largely isolated from each other throughout their interstellar journey, now find themselves pressed into increasingly intimate proximity. The average distance between particles, once measured in meters or kilometers, has shrunk to mere millimeters, then microns, then nanometers. This compression triggers a cascade of physical processes that transform the very nature of the matter within the core. As atoms are pushed closer together, they begin to collide more frequently, transferring kinetic energy from their orbital motions into thermal energy. The temperature, which has remained near absolute zero throughout the millions of years of slow gravitational contraction, suddenly begins to rise in response to this new source of heating. The relationship between compression and heating follows fundamental laws of thermodynamics that operate throughout the universe. As the volume of gas decreases, its temperature must increase to to conserve energy, a principle that governs everything from the operation of refrigerators to the ignition of stellar furnaces. But in the context of stellar birth, this heating serves a crucial purpose. It creates the thermal pressure necessary to slow and eventually halt the gravitational collapse. As the temperature within the core rises from tens of degrees to hundreds, then thousands of degrees, something beautiful begins to happen. The increased thermal motion of atoms creates an outward pressure that starts to compete with gravity's inward pull. For the first time since the collapse began millions of years ago, the stellar embryo begins to experience internal resistance to further contraction. Matter, awakened from its cold slumber, begins to push back against the cosmic forces that have been shaping its destiny. This awakening doesn't happen uniformly throughout the collapsing core. The center, experiencing the greatest compression, heats up fastest and develops the strongest thermal pressure. The outer regions, still relatively cool and sparse, continue to fall inward under gravity's influence. This creates a temperature gradient within the embryonic star, a thermal architecture that will play a crucial role in determining how nuclear fusion eventually ignites and how the star will regulate its energy production throughout its lifetime. At temperatures of a few thousand degrees, the hydrogen gas within the core undergoes its first major phase transition since the collapse began. The molecules of H2 that have dominated the chemistry of the molecular cloud begin to dissociate into individual hydrogen atoms as the thermal energy becomes sufficient to break the molecular bonds. This dissociation actually absorbs energy, temporarily cooling the gas and allowing gravitational compression to continue a bit longer before thermal pressure can fully assert itself. As temperatures continue to rise into the tens of thousands of degrees, an even more dramatic transformation occurs. The hydrogen atoms themselves begin to ionize, with thermal collisions stripping electrons away from atomic nuclei. The core transitions from being a gas of neutral atoms to being a plasma, an electrically conductive state of matter, where positively charged protons and negatively charged electrons move independently through space. This transition to plasma represents a fundamental change in the physics governing the stellar embryo. Electromagnetic forces, which played minimal roles during the neutral gas phase of collapse, now become important players in the drama of stellar birth. Magnetic fields that were frozen into the original molecular cloud can now interact directly with the ionized gas, potentially influencing the rotation and structure of the forming star. The heating process also awakens the cosmic dust grains that have been passengers throughout the collapse. These tiny particles, composed of heavier elements like carbon, silicon, and iron, begin to sublime, transitioning directly from solid to gas. As temperatures rise above a few thousand degrees, this releases additional heating as the vaporization process adds thermal energy to the gas, while also enriching the stellar embryo with the heavier elements that were locked away in solid form during the cold phase of collapse. Meanwhile, radiation begins to play an increasingly important role in the energy budget of the forming star. As temperatures rise, the embryonic star begins to glow with thermal radiation, first in the infrared portion of the electromagnetic spectrum, then gradually shifting toward visible light. As temperatures continue to increase, this radiation carries energy outward from the core, providing another mechanism for regulating the temperature and pressure balance within the stellar embryo. The competition between gravitational compression and thermal pressure creates a delicate balancing act that determines the final structure of the forming star. If thermal pressure becomes too strong too quickly, it can halt gravitational collapse before the core reaches the densities and temperatures necessary for nuclear fusion. If gravitational compression overwhelms thermal pressure, the collapse can continue until the stellar embryo becomes so dense and hot that it overshoots the conditions necessary for stable hydrogen burning. As our stellar embryo approaches the end of this crucial phase, its central temperature rises above 10,000 degrees, then 100,000 degrees, approaching the magical threshold of 10 million degrees, where nuclear fusion of hydrogen becomes possible. The core has now contracted to dimensions comparable to those of a typical star, with a radius of several 100,000 kilometers and a mass approaching that of our Sun. At these extreme conditions, matter exists in a state unlike anything found elsewhere in the universe. Densities are comparable to those in the centers of planets, but temperatures are hotter than the surfaces of stars. Pressures exceed those found in the deepest ocean trenches by factors of billions. In this cosmic crucible, hydrogen nuclei, simple protons, begin to move with such enormous velocities that they can overcome their mutual electrical repulsion and approach close enough for the strong nuclear force to bind them together. The stage is now set for the final transformation that will convert our stellar embryo into a true star. Nuclear fusion, the process that will provide the energy source for billions of years of stable stellar burning, awaits only the final increment of temperature and density that will allow hydrogen to begin fusing into helium on a self-sustaining basis. The patient work of gravity has created the cosmic conditions necessary for the universe's most fundamental energy source to ignite. It is both humbling and beautiful that this awakening of matter from the cold, sparse gas of interstellar space to the hot, dense plasma of a stellar core follows physical laws that we can understand and describe mathematically. The same principles of thermodynamics that govern the operation of steam engines also determine when and how stars are born. The universe reveals itself to be comprehensible to human reason, even in its most extreme and magnificent manifestations. Tonight, somewhere in our galaxy, stellar embryos are undergoing this crucial awakening. Matter that has been patient and cold for millions of years is experiencing the cosmic equivalent of consciousness, the awakening to internal activity, the development of structure and temperature gradients, the beginning of the complex interplay between forces that will govern stellar life for billions of years to come. In the cosmic nursery, where gravity has been patiently gathering matter for millions of years, we now witness one of the universe's most remarkable transitions, the moment when a collapsing cloud of gas transforms into something that can, for the first time, truly be called a stellar object. This is the birth of a protostar, a celestial embryo that carries within its hot, dense core all the potential for billions of years of stellar life, yet hasn't quite learned to sustain the nuclear fires that will define its adult existence. There is something profoundly moving about this moment of cosmic awakening after millions of years of patient gravitational collapse, during which matter has been slowly concentrating and heating. The stellar embryo finally reaches the critical densities where it begins to behave like a coherent, unified object rather than simply a collapsing cloud. It's as if consciousness is dawning within the cosmic material, a first stirring of the complex internal processes that will govern stellar life for eons to come. Picture, if you will, the moment when our collapsing core crosses this invisible threshold. The central regions have now contracted to roughly the size of our solar system, with densities approaching those found in terrestrial materials and temperatures soaring into the tens of thousands of degrees. At these extreme conditions, the hydrogen gas has become fully ionized, creating a plasma where protons and electrons move independently through an electrically charged cosmic soup. The defining characteristic of a protostar is its ability to achieve hydrostatic equilibrium, a delicate balance between the inward pull of gravity and the outward push of thermal pressure. For the first time since collapse began, these opposing forces reach a temporary truce, with thermal pressure strong enough to halt further gravitational contraction, at least in the central regions. The stellar embryo has found its temporary shape, though it will continue to evolve and adjust as it approaches full stellar maturity. This hydrostatic equilibrium creates the first stable structure within what was once a chaotic, collapsing system. The protostar develops a well-defined boundary between its hot, dense core and its cooler, still contracting outer envelope. Energy generated by gravitational compression in the core begins to flow outward through the stellar material, creating temperature and pressure gradients that will eventually establish the complex internal architecture of a mature star. At the heart of the protostar, densities have now reached truly astronomical proportions, perhaps 100 times greater than water, compressed into a sphere that could fit comfortably within the orbit of Mercury. Yet, despite these extreme conditions, the core temperature hasn't quite reached the 10 million degrees necessary to sustain nuclear fusion of hydrogen. The protostar glows with gravitational energy, heat generated by the conversion of gravitational potential energy into thermal energy, but it hasn't yet learned to create energy through nuclear alchemy. This gravitational luminosity gives protostars their distinctive characteristics as observed from Earth. They shine most brightly in the infrared portion of the electromagnetic spectrum, radiating the thermal energy generated by their ongoing contraction. To infrared telescopes, stellar nurseries appear as glowing regions populated by dozens or hundreds of these warm, embryonic objects, each radiating the heat of its own gravitational compression. The structure of a protostar reveals itself to be remarkably complex, with distinct layers that foreshadow the sophisticated internal architecture of mature stars. The core, where matter has reached its highest density and temperature, is surrounded by an envelope of material that is still slowly accreting from the surrounding molecular cloud. This envelope, much larger and cooler than the core, continues to rain matter down onto the central object, adding mass and gravitational energy that further heats the interior. Between the core and the outer envelope lies a transition region where the physics of energy transport undergoes fundamental changes. In the deep interior, energy moves through radiation, photons carrying thermal energy outward from the hot core toward the cooler surface. But in the outer layers, where temperatures are lower and the gas is less ionized, energy transport shifts to convection, with hot gas bubbles rising toward the surface while cooler material sinks back toward the interior. This convective zone plays a crucial role in mixing the protostar's material, ensuring that heavy elements created in previous generations of stars become well distributed throughout the forming object. It also helps transport angular momentum outward, allowing the protostar to shed some of the rotational energy it inherited from the original molecular cloud. Without this mechanism, many protostars would spin so rapidly that centrifugal forces would prevent further contraction. The mass accretion process that feeds protostars creates one of their most spectacular observable features. Accretion disks, as material from the molecular cloud falls toward the protostar. Conservation of angular momentum causes it to spiral inward, forming a flattened disk of hot, glowing matter. These cosmic whirlpools serve as feeding mechanisms, channeling matter from the outer envelope down to the stellar surface in a controlled, gradual process that can continue for millions of years. The accretion disk acts like a cosmic placenta, mediating the flow of material and energy between the protostar and its birth environment. Matter spiraling through the disk heats up due to friction and gravitational compression, often becoming hot enough to glow brightly in visible light. In some cases, these accretion disks can be more luminous than the protostars they feed, creating spectacular celestial displays visible across vast distances of space. As matter spirals inward through the accretion disk, it eventually reaches the stellar surface in a process that releases tremendous amounts of energy. The infalling material strikes the protostar's photosphere at velocities of hundreds of kilometers per second, creating hot spots where the kinetic energy of infall is converted into thermal radiation. These accretion hotspots can create complex brightness variations as the protostar rotates, causing some young stellar objects to appear, to pulse or flicker when observed from Earth. The protostellar phase represents a cosmic adolescence, a period of rapid growth and dramatic change. As the stellar embryo approaches maturity, the central temperature continues to rise as gravitational contraction proceeds in the core, slowly approaching the critical threshold where nuclear fusion can begin. Meanwhile, the mass of the protostar increases as it continues to accrete material from its surrounding disk and envelope, adding fuel for its eventual nuclear awakening. Different protostars evolve at different rates depending on their mass and birth environment. The most massive embryos, containing tens of times the mass of our Sun, evolve rapidly and may reach nuclear ignition in less than 1,000,000 years. These stellar giants will become the brilliant, short-lived stars that dominate their stellar neighborhoods with intense radiation and powerful stellar winds. Smaller protostars, containing only a fraction of the Sun's mass, evolve much more slowly and may remain in the protostellar phase for tens of millions of years before achieving nuclear fusion. The surrounding environment also plays a crucial role in protostellar evolution. Protostars, born in dense stellar clusters, where they compete with numerous siblings for the available gas and dust, may have their growth truncated by the radiation and stellar winds of nearby massive stars. Others, born in relative isolation, may continue accreting material for extended periods, eventually becoming more massive than they would in a crowded stellar nursery. As protostars mature, they begin to clear their immediate environment of the gas and dust that facilitated their birth. The combination of radiation pressure from their surfaces and the onset of weak stellar winds begins to push away the remaining material in their accretion disks and envelopes. This cleaning process marks the transition from the protostellar phase to the pre-main sequence phase, where the young star continues to contract and heat up while no longer actively accreting significant amounts of material. Perhaps the most beautiful aspect of the protostellar phase is how it demonstrates the universe's ability to create order from apparent chaos. What began as a chaotic collapse of diffuse gas has become an organized, structured object with complex internal processes and sophisticated energy transport mechanisms. The protostar represents cosmic potential on the verge of realization, a stellar embryo that carries within it all the ingredients necessary for billions of years of stable nuclear burning. Tonight, throughout our galaxy, thousands of protostars are undergoing this crucial phase of development. Each one represents a unique experiment in stellar formation, shaped by the specific conditions of its birth environment and the cosmic inheritance it received from previous generations of stars. Some will become stable, long-lived stars that will nurture planetary systems for billions of years. Others will become exotic objects, brown dwarfs that never quite achieve nuclear fusion, or massive stars that will live fast and die young in spectacular cosmic explosions. In the quiet depths of space, where these protostars slowly mature in their cosmic nurseries, we witness one of the universe's most fundamental creative processes. Gravity, having gathered the raw materials for stellar birth, now hands off the construction project to the complex interplay of thermodynamics, electromagnetism, and nuclear physics that will govern the remaining phases of stellar evolution. The embryonic giants continue their patient journey toward nuclear awakening, carrying within them the seeds of future planetary systems, and perhaps the very conditions that make life possible. In the cosmic cathedral, where gravity has been composing its grandest symphony for millions of years, we now approach the most transcendent moment in stellar birth, the ignition of nuclear fusion. This is the instant when a protostar, having gathered sufficient mass and compressed its core to unimaginable densities and temperatures, finally achieves the conditions necessary to begin the nuclear alchemy that will transform hydrogen into helium and, in doing so, begin generating its own light. It is the first heartbeat of a star, the moment when gravitational potential energy gives way to nuclear energy as the primary source of stellar luminosity. There is something almost spiritual about this cosmic transition. After millions of years of patient gravitational compression, during which the stellar embryo has glowed only with the heat of its own contraction, the moment finally arrives when hydrogen nuclei in the core begin to overcome their mutual electrical repulsion and fuse together into heavier elements. It's as if the universe has been holding its breath throughout the long protostellar phase, waiting for this moment of nuclear awakening that will sustain the star for billions of years to come. Picture, if you will, the conditions within the stellar core as it approaches this critical threshold. The temperature has now reached 10 million degrees, a heat so intense that it dwarfs any temperature found on planetary surfaces, yet represents just the minimum necessary for nuclear fusion to begin. At these temperatures, hydrogen nuclei move with such enormous velocities that they can penetrate the electrical barrier that normally keeps positively charged particles apart. Approaching close enough for the strong nuclear force to bind them together. The density at the stellar core has reached truly extraordinary proportions, roughly 100 times denser than water, with matter compressed to states that exist nowhere else in the contemporary universe except in the centers of stars. In every cubic centimeter of this stellar plasma, there are more hydrogen nuclei than there are people on Earth, all moving at velocities of thousands of kilometers per second in a cosmic dance of thermal chaos that somehow manages to produce the ordered process of nuclear fusion. The nuclear reactions that power stellar fusion represent one of the universe's most elegant energy production mechanisms. The primary process, known as the proton-proton chain, begins when two hydrogen nuclei collide with sufficient energy to overcome their electrical repulsion. Through a series of nuclear transformations involving positron emission and neutrino production, four hydrogen nuclei are eventually converted into one helium nucleus, releasing energy according to Einstein's famous equation E re mc2. This energy release is both minute and magnificent. Each individual fusion reaction produces only a tiny amount of energy, less than the energy contained in a single grain of sand falling from a table to the floor. Yet in the stellar core, these reactions occur at a rate of roughly 1038 per second, creating a nuclear furnace that produces energy at a rate equivalent to exploding hundreds of millions of hydrogen bombs every second, all contained within a sphere roughly the size of the Earth. The onset of nuclear fusion marks a fundamental transition in the physics governing stellar evolution. For the first time since collapse began, the star has developed an internal energy source that can potentially balance its gravitational contraction. Nuclear fusion provides thermal energy to maintain the high temperatures and pressures necessary to support the star against its own gravity, establishing what astronomers call the main sequence phase of stellar evolution. But this nuclear awakening doesn't happen instantaneously throughout the stellar core. Fusion begins in the very center, where temperatures and densities are highest, then gradually spreads outward as the energy released by initial fusion reactions heats the surrounding material. It's as if a nuclear flame ignites at the stellar heart and slowly burns outward, establishing a self-regulating fusion zone that will eventually encompass a significant fraction of the stellar interior. The self-regulating nature of stellar nuclear fusion represents one of the universe's most sophisticated feedback mechanisms. If the fusion rate increases, the additional energy released heats the core, causing it to expand and cool, which reduces the fusion rate back toward equilibrium. If the fusion rate decreases, the core contracts and heats up, increasing the reaction rate. This natural thermostat allows stars to maintain steady energy production for billions of years. The energy produced by nuclear fusion must now begin its long journey from the stellar core to the surface and eventually out into space. This journey, through layers of hot, dense stellar material, can take tens of thousands of years for individual photons. The gamma rays produced by nuclear reactions are absorbed and re-emitted countless times as they work their way outward, gradually losing energy and shifting toward longer wavelengths as they travel through the stellar interior. As fusion becomes established in the core, the star undergoes its final major structural adjustments. The additional energy source allows it to achieve a new equilibrium between gravitational contraction and thermal pressure, establishing the size, temperature, and luminosity that will characterize its main sequence lifetime. The protostellar phase officially ends, and the object can now be considered a true star, nuclear-powered furnace capable of shining steadily for billions of years. The ignition of nuclear fusion also marks the beginning of stellar nucleosynthesis, the cosmic process by which stars create heavier elements from lighter ones, while the primary fusion reactions convert hydrogen into helium. The extreme conditions in stellar cores also enable the formation of small amounts of lithium, beryllium, and boron. In more massive stars, where core temperatures eventually reach hundreds of millions of degrees, fusion will eventually progress to create carbon, oxygen, silicon, and even heavier elements up to iron. Different stars achieve nuclear ignition under different conditions, creating a diverse population of stellar types. Low-mass stars, containing less than half the mass of our Sun, barely reach the temperature threshold for hydrogen fusion and will burn their fuel so slowly that they can maintain nuclear reactions for hundreds of billions of years. High-mass stars, containing tens of times the Sun's mass, achieve fusion under such extreme conditions that they burn through their nuclear fuel in just a few million years. The transition from gravitational to nuclear energy production also affects the star's interaction with its environment. As nuclear fusion becomes established, the star begins to generate more energetic radiation and develops the first stirrings of stellar winds, streams of charged particles flowing outward from the stellar surface. These phenomena will play increasingly important roles in clearing the star's immediate environment of residual gas and dust from its birth cloud. The neutrinos produced as byproducts of nuclear fusion provide a unique window into the stellar interior. Unlike photons, which can take tens of thousands of years to travel from core to surface, neutrinos interact so weakly with matter that they escape from the stellar core almost instantly, carrying direct information about the nuclear reactions taking place in the star's heart. These ghostly particles, trillions of which pass through every square centimeter of Earth's surface every second, represent stellar heartbeats that we can detect with sophisticated underground neutrino observatories. As our newborn star settles into its nuclear-powered existence, it joins the cosmic community of main sequence stars that populate the galaxy. Its nuclear fires will burn steadily for billions of years, providing a stable energy source that could potentially warm planetary surfaces and drive the complex chemistry necessary for life. The hydrogen fuel that powers these reactions was forged in the first few minutes after the Big Bang, while the star's outer layers contain heavier elements created in previous generations of stars, making each new stellar birth a cosmic recycling event that connects the star to the entire history of the universe. The ignition of nuclear fusion represents more than just a change in energy source. It marks the star's entry into cosmic citizenship. As a nuclear-powered object, it will begin to influence its galactic environment through radiation, stellar winds, and eventually, if it's massive enough, through its explosive death. The heavy elements it creates through nuclear reactions will eventually be returned to the interstellar medium, enriching future generations of stars and planetary systems with the chemical complexity necessary for rocky planets and organic chemistry. Tonight, somewhere in our galaxy, protostars are experiencing their first moments of nuclear awakening. In stellar cores, reaching 10 million degrees for the first time, hydrogen nuclei are beginning their transformation into helium, releasing the first nuclear photons that will eventually illuminate planetary systems and perhaps nurture the emergence of life. These newborn stars join the vast stellar community that lights up the cosmos, each one representing a successful culmination of gravity's patient work and the beginning of a new chapter in the ongoing story of cosmic evolution. As the newborn star settles into its nuclear-powered existence with fusion reactions now sustaining the temperatures and pressures necessary to maintain hydrostatic equilibrium, a remarkable new phenomenon begins to emerge from its surface. Stellar winds, these streams of charged particles flowing outward from the star at velocities that can exceed 1,000 kilometers per second, represent the young star's first attempts to reshape its cosmic environment and clear away the remaining debris from its turbulent birth process. There is something both gentle and powerful about the way stellar winds operate. Unlike the violent explosions that mark the deaths of massive stars, stellar winds represent a more subtle form of cosmic influence, a steady, persistent outflow that works over millions of years to gradually sculpt the space around the newborn star. It's as if the star, having achieved nuclear maturity, now begins to assert its presence in the galaxy by extending its influence far beyond the boundaries of its physical surface. Picture, if you will, the surface of our newly ignited star during the early stages of wind development. The nuclear fusion reactions in the core have established a steady flow of energy outward through the stellar interior, creating temperature and pressure gradients that eventually drive material away from the stellar surface. The star's outer atmosphere, heated to temperatures of millions of degrees by various magnetic and shock processes, begins to expand outward into the surrounding space, carrying with it the chemical signature of the star's composition and nuclear processes. The physics underlying stellar wind formation reveals the sophisticated interplay between electromagnetic forces, thermal pressure, and radiation pressure that governs stellar atmospheres. As photons produced by nuclear fusion work their way outward through the stellar interior, they eventually reach the star's surface and begin to exert radiation pressure on the particles in the stellar atmosphere. For stars more massive than our Sun, this radiation pressure can become strong enough to overcome the star's gravitational pull, driving material away from the surface and into interstellar space. Magnetic fields threading through the stellar atmosphere play an equally important role in wind generation. The star's rotation and convective motions in its outer layers create complex magnetic field configurations that can accelerate charged particles to high velocities and channel them away from the stellar surface along magnetic field lines. These magnetized winds can carry angular momentum away from the star, causing it to spin more slowly over time, a cosmic braking mechanism that helps young stars settle into more stable rotation rates. The composition of stellar winds provides a direct sample of the star's interior chemistry, offering astronomers a way to study nuclear processes occurring deep within stellar cores. The winds carry isotopes of hydrogen and helium that have been processed by nuclear reactions, along with trace amounts of heavier elements, either inherited from the star's birth cloud or created by nuclear fusion in the stellar interiors. By analyzing the chemical composition of stellar winds, astronomers can infer details about stellar structure and evolution that would otherwise remain hidden. As stellar winds encounter the remaining material from the star's birth environment, they create some of the most beautiful and dynamic structures in the cosmos. The interaction between the outflowing stellar particles and the residual gas and dust from the molecular cloud creates shock waves, turbulence, and heating that cause the interstellar material to glow at various wavelengths. These glowing regions, visible to telescopes as emission nebulae, trace the boundaries where stellar winds meet and interact with their birth environments. The clearing process begins close to the star and gradually extends outward over millions of years. Initially, stellar winds can only affect material in the star's immediate vicinity, perhaps within a few astronomical units of the stellar surface. But as the wind continues to flow and interact with the surrounding medium, it creates an expanding bubble of hot, tenuous gas that can eventually grow to encompass regions hundreds of times larger than the original stellar system. This cleaning process is particularly dramatic around massive, luminous stars whose powerful radiation and vigorous stellar winds can create cavities in the interstellar medium spanning dozens of light years. These stellar bubbles, heated to temperatures of millions of degrees by shock waves and stellar radiation, become visible to X-ray telescopes as glowing regions of hot plasma surrounding young stellar associations. The energy injected by stellar winds heats the interstellar medium and can trigger or inhibit star formation in neighboring molecular clouds. For lower mass stars like our Sun, the wind clearing process operates more gently but no less effectively over longer timescales. The early solar wind, enhanced by the Sun's more vigorous magnetic activity during its youth, helped clear the solar nebula of residual gas and dust that might otherwise have been accreted by the forming planets. This cleaning process played a crucial role in determining the final masses and compositions of the planets, particularly the terrestrial worlds of the inner solar system. The temporal evolution of stellar winds reflects the changing conditions within the star as it continues to adjust to its nuclear-powered existence. Young stars often exhibit much stronger and more variable winds than their older counterparts, partly because their magnetic fields are more vigorous and partly because they're still undergoing structural changes as they settle onto the main sequence. These enhanced early winds, sometimes called T Tauri winds, after a class of young stellar objects, can be thousands of times stronger than the winds of mature stars. Stellar winds also play important roles in the chemical evolution of galaxies. By distributing processed material throughout the interstellar medium, while the nuclear fusion reactions in stellar cores create new heavy elements, stellar winds provide a mechanism for dispersing these elements into space, where they can be incorporated into future generations of stars and planetary systems. This process of cosmic recycling ensures that each new generation of stars is slightly more metal-rich than the previous generation, enabling the formation of rocky planets and complex chemistry. The interaction between stellar winds and magnetic fields creates some of the most complex and beautiful phenomena in stellar astronomy. Stars with strong magnetic fields can channel their winds along magnetic field lines, creating collimated outflows that extend for vast distances into space. When these magnetic wind streams interact with each other or with the interstellar medium, They can create intricate structures resembling cosmic sculptures, twisted ribbons, and helical patterns that trace the invisible architecture of stellar magnetic fields. Variable stellar winds can also create time-dependent structures in the surrounding medium. As stars undergo changes in their magnetic activity or rotation rates, their wind properties change accordingly, creating shells and bubbles of material with different densities, temperatures, and chemical compositions. These layered structures preserve a record of the star's activity history and can persist in the interstellar medium for millions of years after they were created. The study of stellar winds in nearby young stars provides crucial insights into the early history of our own solar system. By observing how contemporary stellar winds interact with protoplanetary disks and clear away residual material from star formation, astronomers can reconstruct the processes that shaped our solar system during its first few million years of existence. These observations help explain why our solar system has its current structure and why planetary formation proceeded as it did around the young sun. Perhaps the most beautiful aspect of stellar winds is how they represent a star's first gift to the galaxy. Having spent millions of years gathering material from the interstellar medium during its formation, the newborn star now begins to give back to its cosmic environment, enriching the space around it with processed material and energy. This outflow of stellar matter creates the conditions necessary for future star formation, while also clearing space for the development of planetary systems around the star itself. As stellar winds continue their patient work of clearing and enriching the space around young stars, they prepare the cosmic stage for the next chapter in the ongoing story of cosmic evolution. The cavities they create in molecular clouds can become sites where future star formation occurs, while the material they disperse carries the chemical products of stellar nucleosynthesis to regions where new stars and planetary systems will eventually form. Tonight, throughout our galaxy, stellar winds are flowing outward from thousands of young stars, each one participating in the cosmic circulation system that redistributes matter and energy throughout the interstellar medium. These invisible streams of stellar material represent the beginning of each star's long-term relationship with its galactic environment, a relationship that will continue throughout the star's nuclear lifetime and beyond, connecting it to the ongoing processes of cosmic evolution that shape the structure and chemistry of the universe. In the aftermath of stellar birth, as nuclear fusion establishes itself in the newborn star's core, and stellar winds begin their patient work of clearing the immediate environment, we encounter one of the universe's most remarkable and consequential structures, the protoplanetary disk. This flattened, rotating wheel of gas, dust, and rocky debris represents the leftover material from star formation, cosmic remnants that will soon embark on their own extraordinary journey of aggregation and growth, eventually giving rise to the planets, moons, asteroids, and comets that populate stellar systems throughout the galaxy. There is something almost artistic about the way protoplanetary disks reveal themselves to our telescopes. These cosmic workshops appear as dark silhouettes against the bright backgrounds of stellar nurseries, or as glowing rings of warm dust illuminated by their central stars. Each disk is unique, shaped by the specific conditions of its birth and the characteristics of its parent star, yet all follow similar physical principles as they slowly transform from chaotic debris into ordered planetary systems. Picture, if you will, the protoplanetary disk surrounding our newly born star during the early stages of planetary formation. The disk extends from perhaps a few stellar radii outward to distances of hundreds of astronomical units, a scale that encompasses everything from the orbit of Mercury to regions far beyond Pluto in our own solar system. Within this vast expanse of space, temperatures vary dramatically, from thousands of degrees near the star to just tens of degrees above absolute zero in the outer reaches, creating distinct chemical and physical environments that will determine what types of planetary materials can condense and survive. The structure of a protoplanetary disk reflects the fundamental physics of rotating, gravitating systems. Conservation of angular momentum from the original molecular cloud collapse has flattened the material into a thin disk, with most of the mass concentrated in the central plane where gravity and centrifugal forces achieve balance. The disk rotates according to Kepler's laws, with material closer to the star orbiting faster than material in the outer regions, creating differential rotation that drives complex fluid dynamics throughout the disk. The composition of the disk tells the story of cosmic chemical evolution spanning billions of years. Roughly 99% of the mass consists of hydrogen and helium, the primordial elements forged in the Big Bang and inherited from the interstellar medium. The remaining 1% contains all the heavier elements, from carbon and oxygen to silicon and iron, created in previous generations of stars and dispersed into space through stellar winds and supernova explosions. It's this small fraction of heavy elements that will provide the raw materials for rocky planets and the complex chemistry that makes life possible. Within the disk, cosmic dust grains serve as the fundamental building blocks for planetary construction. These microscopic particles, typically smaller than the particles in cigarette smoke, consist of refractory materials like silicates, carbon compounds, and metallic alloys that can survive the relatively harsh environment near a young star. Each grain represents a tiny construction unit that will eventually be incorporated into larger structures through the patient process of collisional aggregation. The process of planetary formation begins with the gentle collision and sticking of dust grains in the cold, dense regions of the disk. These particles can develop sticky surfaces due to the condensation of volatile compounds like water ice, allowing them to adhere when they collide at the low velocities typical of orbital motion. Over thousands of years, this microscopic construction project gradually builds larger and larger aggregates, cosmic dust bunnies that grow from microns to millimeters to centimeters in size. As these growing particles reach sizes of meters to kilometers, they begin to be affected by their own gravitational attraction, transitioning from a process dominated by surface chemistry and electromagnetic forces to one governed by gravity and orbital mechanics. These intermediate-sized objects, called planetesimals, represent the first true planetary building blocks, solid bodies massive enough to survive collisions and to begin the process of sweeping up smaller debris through gravitational attraction. The formation of planetesimals marks a crucial transition in disk evolution. These early planetary embryos begin to stir up the remaining dust and gas through their gravitational interactions, creating turbulence and heating that can actually inhibit further planet formation in some regions while enhancing it in others. The largest planetesimals grow fastest, initiating a runaway growth process that eventually leads to the formation of planetary cores massive enough to begin accreting atmospheric gases directly from the disk. Temperature gradients within the protoplanetary disk create distinct zones where different types of planetary materials can condense and survive. Close to the star, where temperatures exceed several hundred degrees, only the most refractory materials, metals, and rocky silicates can remain solid. This zone becomes the birthplace of terrestrial planets, small, dense, rocky worlds with thin atmospheres and solid surfaces. Beyond a critical distance from the star, known as the ice line or frost line, temperatures drop sufficiently for water to condense into solid ice. This fundamental transition dramatically increases the amount of solid material available for planet formation, allowing the construction of much more massive planetary cores. These enhanced core masses enable the gravitational capture of substantial atmospheric envelopes from the surrounding gas disk, leading to the formation of gas giant planets like Jupiter and Saturn. Even farther from the star, additional ice lines mark the condensation temperatures of other volatile compounds: ammonia, methane, carbon monoxide, and nitrogen. Each of these transitions provides additional solid material for planetary construction, enabling the formation of ice, giant planets, and the diverse populations of small bodies that inhabit the outer regions of planetary systems. The gravitational influence of forming planets creates remarkable structures within protoplanetary disks. Massive planetary embryos can open gaps in the disk material through their gravitational perturbations, creating ring-like structures that astronomers can observe directly with powerful telescopes. These gaps and rings trace the locations where planets are actively forming, providing real-time views of planetary construction in action around other stars. The interaction between disk material and forming planets also drives planetary migration, the process by which planets can change their orbital distances over time. Gravitational interactions with disk gas can cause planets to spiral inward toward their star or outward toward the disk's edge, dramatically altering the architecture of planetary systems during their formation phase. This migration process helps explain the diversity of planetary system architectures observed around other stars, including the existence of hot Jupiters and other exotic planetary configurations. The chemical evolution of protoplanetary disks involves complex interactions between gas phase and solid phase materials. As dust grains collide and stick together, they can incorporate volatile compounds that condense on their surfaces, creating chemically complex particles that preserve records of disk conditions and evolution. The organic compounds formed in these cosmic chemistry laboratories may provide some of the prebiotic materials necessary for the eventual emergence of life on suitable planetary surfaces. The lifetime of protoplanetary disks sets important constraints. On planetary formation timescales, observations of disks around stars of different ages show that most disks dissipate within a few million years, driven away by stellar winds, radiation pressure, and the gravitational perturbations of forming planets. This relatively short timescale means that the major phases of planetary formation, from dust aggregation to gas giant formation, must occur rapidly by geological standards. Different stellar masses create protoplanetary disks with different characteristics and evolutionary timescales. Massive stars, with their intense radiation and powerful stellar winds, can photoevaporate disk material rapidly, limiting the time available for planet formation and potentially preventing the formation of gas giant planets. Low-mass stars, with their gentler radiation and weaker winds, can maintain their disks for longer periods, potentially allowing more time for complex planetary architectures to develop. The diversity of observed protoplanetary disks around other stars reveals the wide range of initial conditions that can lead to planetary system formation. Some disks show clear evidence of ongoing planetary formation, with gaps, rings, and asymmetric structures that trace the gravitational influence of embryonic planets. Others appear smooth and featureless, suggesting that planet formation either hasn't begun or is occurring in ways that don't create observable disk structures. As protoplanetary disks evolve and dissipate, they leave behind the planetary systems that will persist for billions of years. The final architecture of each system, the number, masses, and orbital characteristics of its planets, reflects the complex interplay between initial disk conditions, stellar properties, and the chaotic dynamics of planetary formation. Each planetary system represents a unique outcome of this cosmic construction project, shaped by the specific conditions present during its formation epoch. Perhaps the most beautiful aspect of protoplanetary disks is their role as cosmic nurseries, where the raw materials of stellar birth are transformed into the complex, organized structures that make up planetary systems. From the chaotic debris of star formation emerges the ordered architecture of orbital motion, the chemical complexity of planetary compositions, and the potential for the emergence of life itself. Tonight, around stars throughout our galaxy, protoplanetary disks are continuing their patient work of planetary construction. In some systems, the first planetesimals are beginning to form from aggregating dust grains. In others, massive planetary cores are accreting their atmospheric envelopes from the surrounding gas. Each disk represents a laboratory where the universe experiments with the countless possible configurations that planetary systems can adopt, creating the cosmic diversity that makes each stellar system a unique world unto itself. In the cosmic theaters, where stellar birth unfolds across millions of years, there exists a fundamental challenge for human observers. The very dust and gas that provide the raw materials for star formation also shroud the process in an impenetrable veil of darkness. Visible light, which carries the stories of mature stars across vast distances of space, finds itself scattered and absorbed by the microscopic grains that populate molecular clouds, leaving these stellar nurseries hidden from our optical telescopes like cosmic mirages that fade when we try to observe them directly. Yet the universe, in its infinite generosity, provides other windows through which we can witness the silent birth of stars. In the longer wavelengths of infrared radiation and radio waves, the cosmic dust that blocks visible light becomes not an obstacle, but a guide glowing with thermal emission that traces the temperature, density, and chemical composition of stellar nurseries with exquisite precision. It's as if nature has provided us with cosmic X-ray vision, allowing us to peer through the veils of dust and witness creation in action. There is something almost magical about the way radio telescopes reveal the invisible architecture of molecular clouds. These enormous dishes, some spanning hundreds of meters across, capture radio waves emitted by molecules floating in the cold depths of space, signals so faint that the total energy collected by all radio telescopes in history amounts to less than the energy of a single snowflake falling to Earth. Yet from these whispered radio transmissions, astronomers can reconstruct three-dimensional maps of stellar nurseries, tracing the flows of gas, the birth of protostars, and the complex chemistry occurring in regions where temperatures hover just above absolute zero. Picture, if you will, the radio signature of a molecule as simple as carbon monoxide drifting through a molecular cloud. As this molecule rotates and vibrates in the frigid darkness, it emits radio waves at very specific frequencies, cosmic radio stations that broadcast the conditions of their local environment. The frequency of these emissions reveals the temperature of the gas, while their intensity indicates the density of molecules. Most remarkably, the Doppler shift of these radio waves, the slight change in frequency caused by the motion of the gas, allows astronomers to measure the three-dimensional velocity field within molecular clouds, revealing currents, turbulence, and the gravitational flows that channel material toward forming stars. The development of radio astronomy in the mid-20th century opened an entirely new chapter in our understanding of stellar birth. Suddenly, astronomers could observe molecular clouds in their full three-dimensional glory, mapping the distribution of different chemical species and tracing the complex motions that govern how matter flows from diffuse clouds toward dense stellar cores. Each molecular species, carbon monoxide, ammonia, water vapor, methanol, broadcasts at its own characteristic frequencies, creating a cosmic symphony that tells the story of temperature, density, and chemistry throughout the star-forming regions. Radio observations have revealed that molecular clouds possess intricate internal structure that would be completely invisible to optical telescopes. Dense cores, where stars are actively forming, appear as bright radio sources, while the surrounding gas shows complex filamentary patterns that trace the gravitational flows feeding the stellar nurseries. The radio maps reveal turbulent motions, magnetic field structures, and the subtle gravitational perturbations that trigger star formation, cosmic weather patterns that operate on scales of light years and timescales of millions of years. Infrared astronomy provides another crucial window into the hidden processes of stellar birth. The cosmic dust that absorbs visible starlight heats up and re-radiates this energy at longer infrared wavelengths that can penetrate through the dusty veils of molecular clouds. Infrared telescopes, both ground-based observatories equipped with sophisticated cooling systems and space-based instruments that operate above Earth's absorbing atmosphere, can detect this thermal glow and use it to map the temperature distribution throughout star-forming regions. The infrared view of stellar nurseries reveals a cosmic thermal landscape where different regions glow with different intensities, depending on their temperature and dust content. Warm areas, heated by nearby protostars or young stars, appear bright in infrared images, while cooler regions remain dark and mysterious. By observing at multiple infrared wavelengths, astronomers can determine not just the temperature of dust grains, but also their size distribution and chemical composition, providing insights into the materials available for planetary formation. Modern infrared surveys have cataloged thousands of stellar nurseries throughout our galaxy, creating comprehensive maps of star formation activity that reveal how stellar birth proceeds in different galactic environments. These surveys show that star formation follows the spiral structure of our galaxy, with stellar nurseries concentrated in the spiral arms where molecular clouds encounter the gravitational perturbations that trigger their collapse into new stars. The combination of radio and infrared observations creates remarkably detailed portraits of individual star-forming regions. Radio telescopes trace the cold molecular gas that provides the raw material for stellar birth, while infrared observations reveal the warm dust heated by protostars and young stars. Together, these complementary techniques allow astronomers to follow the entire progression from cold, dark, molecular clouds through the formation of protostars to the emergence of stellar nurseries populated by newborn stars. Interferometric radio astronomy, which combines signals from multiple radio telescopes to create instruments with effective diameters spanning continents, has achieved angular resolution fine enough to observe individual protostellar systems in nearby molecular clouds. These observations can trace the rotation of infalling gas around forming protostars, map the structure of protostellar disks, and even detect the radio emission from stellar winds and jets emanating from young stellar objects. The development of submillimeter astronomy, which operates at wavelengths between radio and infrared, has opened yet another window into stellar birth. At these wavelengths, astronomers can observe the thermal emission from cold dust grains and trace the distribution of molecular species that exist only in the coldest regions of space. Submillimeter observations have revealed that many molecular clouds contain networks of dense filaments that channel material towards star-forming cores, suggesting that stellar birth follows preferred pathways through the galaxy's molecular medium. Space-based infrared telescopes have revolutionized our understanding of stellar nurseries by providing clear views unobstructed by Earth's atmosphere. The Spitzer Space Telescope revealed intricate bubble structures blown by stellar winds around young massive stars, while the Herschel Space Observatory mapped the cold dust throughout nearby molecular clouds with unprecedented detail. These missions have shown that star formation is a remarkably inefficient process, with only a small fraction of molecular cloud material actually being converted into stars. The study of polarized radio and infrared emission has unveiled the role of magnetic fields in controlling star formation. Cosmic dust grains tend to align with magnetic field lines, creating polarized emission that traces the magnetic architecture of molecular clouds. These observations show that magnetic fields can both channel gas flows towards star-forming regions and provide support against gravitational collapse, playing crucial roles in determining when and where stellar birth occurs. Multi-wavelength observations that combine radio, infrared, and other wavelengths have revealed that star formation is a complex, multi-scale process that involves the interaction of turbulence, magnetic fields, gravity, and stellar feedback across enormous ranges of spatial scale, from galaxy-wide spiral density waves that trigger molecular cloud formation to the sub-astronomical unit scales where protoplanetary disks form around individual protostars. The star formation process connects the largest and smallest structures in the universe. The development of radio and infrared detector arrays has enabled large-scale surveys that can monitor star formation across entire galaxies. These surveys have shown that the rate of star formation in galaxies depends on their total molecular gas content, their internal dynamics, and their interactions with neighboring galaxies. Young galaxies in the early universe appear to have formed stars much more rapidly than contemporary galaxies, suggesting that star formation efficiency has evolved over cosmic time. Perhaps the most beautiful aspect of radio and infrared astronomy is how these techniques reveal the hidden connections between stars, their birth environments, and the larger galactic ecosystem. The same molecular clouds that give birth to stars also serve as repositories for the heavy elements created by previous stellar generations, while the stellar winds and supernova explosions of young stars shape the conditions for future star formation. Radio and infrared observations trace these connections across vast ranges of space and time, revealing star formation as an ongoing galactic cycle of birth, death, and regeneration. The combination of improved detector sensitivity, advanced data processing techniques, and international collaborations has created a golden age for the study of stellar nurseries. Large radio telescope arrays like ALMA in the Atacama Desert and infrared space missions provide unprecedented views of star formation in action, allowing astronomers to witness processes that unfold over millions of years, but leave their signatures in the electromagnetic radiation that reaches our detectors today. Tonight, radio and infrared telescopes around the world and in space continue their patient vigil, collecting the faint signals that tell the stories of stellar birth in distant molecular clouds. Each photon and radio wave carries information about temperature, density, motion, and chemistry from cosmic construction sites where gravity is building the next generation of stars. Through these invisible messengers, we can witness the universe's ongoing creative work, connecting our understanding of stellar birth to the broader cosmic story of which we are all a part in the quiet hum of supercomputer centers around the world. A different kind of stellar birth is taking place here in climate-controlled rooms filled with processors operating at speeds of trillions of calculations per second. Astronomers are creating virtual universes where the formation of stars can be studied, understood, and predicted with a precision that would be impossible through observations alone. These computational laboratories represent one of humanity's most sophisticated attempts to understand the cosmic processes that shape our universe, translating the fundamental laws of physics into mathematical models that can simulate millions of years of stellar evolution in a matter of hours. There is something almost alchemical about the way computer simulations transform abstract mathematical equations into vivid three-dimensional models of cosmic creation. The same physical laws that govern the behavior of gas, gravity, and magnetic fields in real molecular clouds are encoded into computational algorithms that can follow the evolution of virtual star-forming regions through time. What emerges from these calculations are digital universes where astronomers can witness the complete life cycle of stellar nurseries, from the initial collapse of molecular clouds through the birth of stars and the dispersal of their birth environments. Picture, if you will, the moment when a computational astrophysicist begins a new simulation of star formation. The process starts with the creation of a virtual molecular cloud, perhaps a cube of space, several light years on each side, filled with millions of computational particles that represent the gas and dust of a stellar nursery. Each particle carries information about its position, velocity, temperature, density, and chemical composition, along with the gravitational forces it experiences from all of its neighbors. The mathematical foundation of these simulations rests on equations that have been known for centuries. Newton's laws of gravitation and motion, the laws of thermodynamics, the principles of fluid dynamics. Yet solving these equations for systems containing millions or billions of interacting particles requires computational resources that have only become available in recent decades. Modern simulations must account not just for gravity, but for the complex physics of radiative heating and cooling, magnetic field evolution, turbulent gas dynamics, and the feedback effects of stellar winds and radiation from newly formed stars. As the simulation begins, the virtual molecular cloud starts to evolve according to the same physical processes that govern real stellar nurseries. Gravity pulls particles together, increasing local densities and triggering the formation of dense cores where virtual protostars will eventually form. Turbulent motions, initialized to match observations of real molecular clouds, create eddies and flows that enhance star formation in some regions while inhibiting it in others. Magnetic fields thread through the computational domain, providing additional structure and resistance to gravitational collapse. The beauty of computational star formation lies in its ability to reveal processes that operate on scales and timescales that make direct observation challenging. While real stellar birth unfolds over millions of years, a computer simulation can compress this evolution into timescales that human researchers can study and analyze. While real molecular clouds span many light years and contain regions with vastly different physical conditions, computational models can zoom in on individual forming stars while maintaining awareness of their larger galactic context. Modern simulations have revealed that star formation is an inherently chaotic and unpredictable process, despite being governed by well-understood physical laws. Small changes in initial conditions, slight variations in density, temperature, or turbulent motion can lead to dramatically different outcomes in terms of the number, masses, and spatial distribution of stars that eventually form. This computational insight has profound implications for understanding why different molecular clouds produce different stellar populations and why star formation efficiency varies so dramatically across the galaxy. The incorporation of stellar feedback into computational models has proven particularly illuminating. When virtual protostars reach the point of nuclear ignition in a simulation, they begin to heat their surroundings through radiation and drive material away through stellar winds. just as real stars do. These feedback processes can halt star formation in parts of the molecular cloud, creating self-regulating systems where the stars themselves control how many additional siblings can form in their birth environment. High-resolution simulations have provided unprecedented insights into the formation of stellar clusters and associations. By following the evolution of molecular clouds through their entire star-forming lifetimes, computational models have shown how stellar nurseries develop hierarchical structure, with stars forming in groups and subgroups that reflect the initial density structure of their parent clouds. These simulations help explain the observed clustering properties of young stars and provide predictions about how stellar associations will evolve over time. The computational study of protoplanetary disk formation has benefited enormously from high-resolution simulations that can follow the collapse of individual stellar cores while simultaneously modeling the formation of rotating disks around the central protostars. These models have revealed how magnetic fields, turbulence, and rotation combine to determine the size, mass, and structure of protoplanetary disks, providing crucial insights into the initial conditions for planetary formation. Magnetohydrodynamic simulations, which include the complex physics of plasma and magnetic field evolution, have unveiled the crucial role that magnetic fields play in regulating star formation. These computational models show how magnetic fields can both support molecular clouds against gravitational collapse and channel gas flows towards star-forming regions along field lines. The simulations reveal that the orientation and strength of magnetic fields can dramatically affect the efficiency and timeline of stellar birth. Large-scale galactic simulations have placed individual star-forming regions into their broader cosmic context, showing how galaxy-wide processes like spiral density waves, galactic collisions, and supermassive black hole activity can trigger or inhibit star formation across entire galactic disks. These models help explain the observed correlations between galaxy properties and star formation rates, revealing star formation as a galaxy-scale phenomenon that connects the smallest scales of stellar birth to the largest scales of cosmic structure. The development of adaptive mesh refinement techniques has allowed simulations to achieve unprecedented dynamic range, simultaneously modeling the large-scale structure of molecular clouds and the small-scale physics of individual protostellar cores. These computational advances have made it possible to study how processes operating on vastly different scales interact to determine the overall efficiency and outcomes of star formation. Computational astrochemistry models track the formation and destruction of molecules throughout simulated star-forming regions, providing predictions about the chemical signatures that should be observable in real molecular clouds. These models have proven invaluable for interpreting radio astronomical observations and for understanding how the chemical complexity of the universe evolves as gas cycles between the interstellar medium and stellar interiors. Population synthesis models use the outputs of detailed star formation simulations to predict the observable properties of stellar populations and galaxies. By following the evolution of simulated stellar nurseries through time and adding up the contributions from stars of different masses and ages, These models create synthetic observations that can be compared directly with telescopic surveys of star-forming regions. The increasing sophistication of computational models has led to the development of virtual observatories, where simulated molecular clouds can be observed using the same techniques that astronomers apply to real stellar nurseries. These synthetic observations allow direct comparisons between simulation predictions and observational data, providing crucial tests of our theoretical understanding of star formation physics. Machine learning techniques are beginning to revolutionize computational star formation studies by enabling the analysis of simulation datasets that are too large and complex for traditional analysis methods. Neural networks trained on simulation outputs can identify patterns in star formation that might be missed by human researchers, potentially revealing new insights into the physical processes that govern stellar birth. The computational study of star formation has also provided crucial insights into the role of turbulence in molecular clouds. Simulations show that turbulent motions can both trigger star formation through shock compression and inhibit it by providing additional pressure support against gravitational collapse. Understanding this balance has proven crucial for explaining the observed inefficiency of star formation in molecular clouds. Perhaps the most beautiful aspect of computational star formation is how these virtual laboratories allow us to conduct controlled experiments on cosmic processes that would be impossible to study otherwise. By running multiple simulations with different initial conditions or physical parameters, computational astrophysicists can isolate the effects of individual physical processes and understand how they combine to produce the rich phenomenology of observed stellar nurseries. As computational power continues to increase and simulation techniques become more sophisticated, these virtual cosmic laboratories promise to provide even deeper insights into the processes that govern stellar birth. Future simulations may be able to follow a star formation from the initial collapse of molecular clouds all the way through the formation of planetary systems, connecting the physics of stellar birth to the conditions that make life possible. Tonight, in computational centers around the world, supercomputers continue their tireless work of simulating the birth of stars in digital universes that exist only as patterns of electrical charge in silicon memory. These virtual stellar nurseries, governed by the same physical laws that operate in real molecular clouds, provide windows into cosmic processes that span scales from individual atoms to entire galaxies, revealing the mathematical beauty underlying the universe's most fundamental creative acts in the cosmic tapestry that spans billions of years and encompasses scales from individual atoms to galactic superclusters. Stellar birth emerges not as an isolated phenomenon, but as the fundamental process that drives the evolution and enrichment of entire galaxies. Each molecular cloud that collapses to form new stars participates in a galactic recycling program that has been operating for nearly the entire history of the universe, transforming the simple hydrogen and helium of the Big Bang into the complex chemical elements that make rocky planets and organic chemistry possible. There is something profoundly moving about contemplating how the silent birth of stars connects to the grandest scales of cosmic evolution. Every star that ignites nuclear fusion in its core begins a journey that will eventually return processed material to the galactic medium, contributing to the slow but inexorable chemical enrichment that transforms galaxies from simple collections of primordial gas into complex ecosystems capable of nurturing planetary systems and perhaps life itself. Picture, if you will, our galaxy as it existed 10 billion years ago, when the universe was less than a quarter of its current age. The Milky Way was smaller then, perhaps half its current size, and its gas was composed almost entirely of hydrogen and helium, the elemental legacy of Big Bang nucleosynthesis. Heavy elements like carbon, oxygen, silicon, and iron existed only in trace amounts, having been created in the nuclear furnaces of the very first generation of stars that had formed and died in the early universe. In this ancient galactic environment, star formation proceeded under very different conditions than we observe today. The absence of dust grains, which form from heavy elements, made it more difficult for gas clouds to cool and collapse, requiring larger initial masses to achieve gravitational instability. The first stars were likely much more massive than typical stars today, burning through their nuclear fuel rapidly and ending their lives in spectacular supernova explosions that scattered the first heavy elements into the interstellar medium. Each generation of stellar birth and death has added to the galaxy's chemical complexity through a process astronomers call galactic chemical evolution. When massive stars exhaust their nuclear fuel and explode as supernovas, they release into space not only the heavy elements created during their lifetimes, but also new elements forged in the extreme conditions of the supernova explosion itself. Elements heavier than iron, gold, platinum, uranium are created primarily in these cosmic catastrophes and in the collisions of neutron stars, making every atom of these elements a relic of ancient stellar deaths. The pattern of chemical enrichment across the galaxy reveals the history of star formation in different galactic regions. The central bulge, where star formation was most active in the early universe, shows high concentrations of elements like oxygen and magnesium that are produced by massive, short-lived stars. The outer disk regions, where star formation has proceeded more gradually over cosmic time, show different chemical signatures that reflect the contributions of both massive stars and intermediate mass stars that evolve more slowly. The rate of star formation in galaxies is intimately connected to their supply of cold molecular gas, the raw material from which new stars condense. As star formation converts gas into stars, it gradually depletes the reservoir available for future stellar birth, leading to a natural decline in star formation rates over cosmic time. This process is moderated by the infall of fresh gas from the intergalactic medium and by the recycling of material from dying stars, creating a complex balance that determines how long galaxies can continue forming new stars. Stellar feedback, the energy and momentum injected into the interstellar medium by stellar winds, radiation, and supernova explosions, plays a crucial role in regulating galactic evolution. Young, massive stars can create enormous bubbles of hot gas that expand into the surrounding medium, potentially driving galactic-scale winds that carry enriched material out of the galaxy entirely. This process can shut down star formation in small galaxies, while larger galaxies with deeper gravitational potential, wells can retain most of their processed material. The spiral structure that characterizes disk galaxies, like our own Milky Way, is both shaped by and shapes the process of star formation. Spiral density waves that propagate through galactic disks compress molecular clouds as they pass, triggering episodes of star formation that trace out the spiral pattern. The massive stars born in these spiral arms live fast and die young, enriching the local interstellar medium with heavy elements. Before the region rotates away from the spiral pattern, the study of galactic archaeology, using the chemical compositions of old stars to reconstruct the history of galactic evolution, has revealed that the Milky Way has experienced a complex history of star formation, including periods of enhanced activity triggered by mergers with smaller galaxies. Different stellar populations in our galaxy carry chemical signatures that tell stories of ancient galactic collisions, episodes of rapid star formation, and the gradual buildup of heavy elements over billions of years. Observations of galaxies at different distances, and therefore different epochs in cosmic history, provide direct views of how galactic evolution has proceeded over time. Distant galaxies, seen as they were billions of years ago, show much higher star formation rates than contemporary galaxies, suggesting that the universe was more active in producing new stars during its youth. These observations reveal that the peak epoch of star formation occurred when the universe was roughly a quarter of its current age. The relationship between galaxy mass and star formation efficiency reveals fundamental aspects of how cosmic structure formation connects to stellar birth. More massive galaxies, with their deeper gravitational potential wells and larger gas reservoirs, have been more effective at forming stars over cosmic time. However, the most massive galaxies appear to have shut down their star formation relatively early, possibly due to feedback from their central supermassive black holes. The chemical gradients observed across galactic disks, with higher heavy element abundances toward galactic centers, reflect the inside-out growth pattern of disk galaxies. Star formation began earliest and proceeded most rapidly in the central regions, where gas densities were highest and orbital timescales were shortest. The outer regions formed more recently through the accretion of less chemically evolved material from the galactic halo and intergalactic medium. Galactic encounters and mergers can dramatically affect star formation rates and chemical evolution patterns. When galaxies collide, the gravitational torques generated by their interaction can drive gas toward the galactic centers, triggering intense episodes of star formation called starbursts. These events can consume a galaxy's gas reservoir in a geologically short time, transforming spiral galaxies into elliptical systems with little ongoing star formation. The role of dark matter in galactic evolution provides the gravitational scaffolding upon which all star formation ultimately depends. Dark matter halos determine the masses and spatial distributions of galaxies, influencing their ability to retain gas and form stars over cosmic time. The hierarchical assembly of dark matter structure drives the merger history of galaxies and determines when and where the most dramatic episodes of a star formation occur. Environmental effects also play important roles in galactic chemical evolution. Galaxies in dense clusters experience ram pressure stripping as they move through the hot intracluster medium, which can remove their gas reservoirs and halt star formation. Conversely, galaxies in less dense environments may continue forming stars for much longer periods, leading to different evolutionary outcomes. The production and distribution of different chemical elements by various types of stars creates a complex web of galactic chemical evolution. Type 2 supernovas from massive stars produce oxygen, neon, and magnesium on timescales of millions of years. Type Ia supernovas from white dwarf explosions contribute iron peak elements on timescales of billions of years. Asymptotic giant branch stars contribute carbon and nitrogen through stellar winds over intermediate timescales. Modern surveys that measure the chemical abundances of millions of stars across the galaxy are revealing the detailed history of galactic chemical evolution with unprecedented precision. These studies show that chemical enrichment has not proceeded uniformly across the galaxy, but has followed complex patterns related to stellar migration, gas flows, and the varying efficiency of star formation in different galactic environments. Perhaps the most beautiful aspect of galactic chemical evolution is how it connects the intimate processes of stellar nuclear fusion to the cosmic scale evolution of the universe itself. Every carbon atom in your body was forged in the core of a dying star and expelled into space to eventually be incorporated into the molecular cloud that gave birth to our solar system. The calcium in your bones was created in supernova explosions that helped trigger the formation of subsequent generations of stars. The ongoing cycle of stellar birth, life, and death ensures that galaxies continue to evolve chemically even today. In stellar nurseries throughout the Milky Way, new stars are being born from gas that has been enriched by countless previous generations of stellar evolution. These young stars will eventually contribute their own nuclear products to the galactic medium, continuing the cosmic cycle that gradually transforms the universe from its simple initial state into the chemically complex cosmos we observe today. Tonight, across the observable universe, billions of galaxies continue their slow chemical evolution through the birth and death of stars. Each stellar nursery participates in this cosmic recycling program, transforming hydrogen into heavier elements and gradually building the chemical complexity that makes rocky planets, organic molecules, and ultimately life itself possible. In the silent birth of stars, we witness not just individual acts of cosmic creation, but the fundamental process that drives the evolution of the universe toward ever greater complexity and beauty. In the cosmic symphony of stellar birth, where gravity composes new stars from the ethereal matter of molecular clouds, lies embedded the profound question that connects astronomical processes to the deepest mysteries of existence. Does the formation of stars and their attending planetary systems create the conditions necessary for life to emerge elsewhere in the universe? As we have followed the journey from cold molecular clouds to nuclear burning stars surrounded by protoplanetary disks, we have been tracing not just the formation of cosmic objects, but the construction of potential cradles for biology, consciousness, and intelligence. There is something deeply moving about the realization that every step in the stellar birth process we have explored creates conditions that could potentially nurture life. The heavy elements, forged in previous generations of stars, provide the raw materials for rocky planets and complex chemistry. The protoplanetary disks that form around newborn stars contain the ingredients for diverse planetary systems. The nuclear fusion that ignites in stellar cores provides stable energy sources that could warm planetary surfaces for billions of years. In the silent birth of stars, the universe is conducting countless experiments in habitability. Picture, if you will, a newly formed star settling into its main sequence existence, surrounded by a protoplanetary disk that is beginning the process of planetary construction. Within this cosmic construction site, different regions of the disk offer different possibilities for habitability. Close to the star, where temperatures are high and only refractory materials can condense, small rocky planets may form, worlds that could potentially develop atmospheres and surface conditions suitable for liquid water if they orbit at the right distance from their parent star. The concept of the habitable zone, sometimes called the Goldilocks zone, represents a fundamental connection between stellar properties and the potential for life. This is the range of orbital distances around a star where temperatures are just right for liquid water to exist on a planetary surface, not so close that water boils away, not so far that it freezes permanently. The location and extent of this zone depend intimately on the star's mass, luminosity, and evolutionary state, all of which were determined during the stellar formation process we have been exploring. Different types of stars create very different habitable environments for potential life. Massive, luminous stars burn through their nuclear fuel so rapidly that their habitable zones may not persist long enough for complex life to evolve on any planets that might form. These stellar giants also produce intense ultraviolet radiation that could sterilize planetary atmospheres, making them challenging environments for biology. Red dwarf stars, the most common stellar type in the galaxy, burn so slowly and steadily that their habitable zones could remain stable for hundreds of billions of years, longer than the current age of the universe. The search for exoplanets has revealed an astounding diversity of planetary systems that exceeds anything astronomers imagined before the first confirmed discoveries in the 1990s. Hot Jupiters, orbiting closer to their stars than Mercury orbits the Sun. Super Earths, with masses several times that of our planet. Planets orbiting binary star systems, where two suns rise and set in alien skies. Each discovery expands our understanding of how the stellar formation process can lead to different planetary outcomes and different possibilities for habitability. The timing of planetary formation relative to stellar evolution creates complex relationships between stellar properties and habitability. Young stars tend to be more magnetically active than their older counterparts, producing powerful flares and energetic particle radiation that could strip away planetary atmospheres or sterilize surface environments. However, this same stellar activity might also provide the energy needed to drive atmospheric chemistry and potentially the origin of life itself. The chemical composition of stars, inherited from their birth, molecular clouds, and determined by billions of years of galactic chemical evolution, directly influences the potential habitability of their planetary systems. Stars with higher abundances of heavy elements can form more massive, rocky planets and more chemically diverse planetary systems. The The presence of specific elements like carbon, oxygen, and nitrogen in stellar systems determines whether complex organic chemistry is possible on their planets. Recent discoveries have shown that planetary systems can form around stars with a wide range of masses, ages, and chemical compositions, suggesting that the processes we have traced from molecular clouds to stellar birth are remarkably efficient at creating diverse planetary environments. Some of the most intriguing discoveries include planets orbiting ancient stars that formed when the galaxy was much younger and less chemically enriched, suggesting that potentially habitable worlds might have existed for most of cosmic history. The study of protoplanetary disks around young stars provides direct insights into how planetary systems form and what factors determine their final architectures. Observations of gaps, rings, and asymmetric structures in these disks reveal where planets are actively forming, while spectroscopic studies of disk chemistry show what elements are available for planetary construction. These observations help astronomers understand which types of stellar nurseries are most likely to produce potentially habitable worlds. The role of stellar variability in habitability represents an active area of research that connects stellar physics to astrobiology. Stars undergo changes in luminosity, magnetic activity, and stellar wind properties over their lifetimes, creating evolving conditions for any planets in their systems. Understanding how these stellar changes affect planetary climates and atmospheres is crucial for assessing the long-term habitability of exoplanetary systems. The discovery of Earth-sized planets in the habitable zones of nearby stars has opened new possibilities for detailed studies of exoplanetary atmospheres and surface conditions. Future space-based telescopes will be able to analyze the chemical compositions of exoplanetary atmospheres, searching for biosignatures, chemical indicators that could only be produced by living organisms. These studies will directly test whether the stellar formation processes we have explored actually lead to the emergence of life. The search for potentially habitable exoplanets has also revealed the importance of planetary system architecture in determining habitability. The presence of massive planets in outer orbits can protect inner terrestrial worlds from comet impacts, while the absence of such protection might lead to more frequent extinction events. The orbital characteristics of planets, their eccentricities, inclinations, and resonant relationships all influence climate stability and the potential for long-term habitability. Stellar multiplicity adds another layer of complexity to the habitability question. Since roughly half of all stars exist in binary or multiple star systems, understanding how planets form and evolve in these complex gravitational environments is crucial for assessing the prevalence of potentially habitable worlds. Some binary star systems may offer enhanced stability for planetary orbits, while others might be too chaotic to maintain stable climates over geological timescales. The study of stellar formation in different galactic environments reveals that habitability prospects may vary significantly across the galaxy. The central regions, with their high stellar densities and frequent supernova explosions, might be too hazardous for long-term biological evolution. The outer galactic regions, with their lower abundances of heavy elements, might lack the chemical complexity necessary for robust planetary formation. The galactic habitable zone, the range of galactic radii, where conditions are most favorable for life may encompass only a fraction of the galaxy's stellar population. Recent discoveries of potentially habitable planets around red dwarf stars have raised intriguing questions about the relationship between stellar formation, efficiency, and habitability. Red dwarfs are the most common stellar type in the galaxy and have the longest main sequence lifetimes, potentially providing stable environments for billions of years. However, their formation process and early evolution create challenges for habitability, including strong magnetic activity during their youth and tidal locking of close-in planets. The temporal evolution of habitability in planetary systems connects directly to the stellar evolution processes that begin during star formation. As stars age and evolve, their habitable zones migrate outward, potentially bringing previously frozen worlds into habitable temperature ranges, while rendering formerly habitable planets too hot for life. Understanding these evolutionary processes is crucial for assessing where and when life might emerge and thrive in the galaxy. Perhaps the most profound implication of exoplanet discoveries is how they illuminate the cosmic significance of the stellar formation processes we have explored. Every molecular cloud collapse, every protostellar disk, every episode of planetary formation represents an opportunity for the universe to create new environments where complexity, chemistry, and potentially biology can flourish. The silent birth of stars is also the silent birth of possibilities for life. The ongoing search for life beyond Earth represents the ultimate test of whether the cosmic processes of stellar and planetary formation actually lead to the emergence of biology. As our observational capabilities continue to improve, we may soon detect chemical signatures of life in the atmospheres of exoplanets, providing direct evidence that the universe's talent for creating complexity extends from stars and planets to living organisms. Tonight, around stars throughout the galaxy, planetary systems continue to form and evolve, each representing a unique experiment in habitability conducted by the universe itself. Some of these worlds may already harbor life, perhaps for billions of years. Others may be in the early stages of developing the complex chemistry that could eventually give rise to biology. In the silent birth of stars and the formation of their planetary companions, we witness not just the creation of cosmic structure, but the universe's ongoing exploration of its own potential for consciousness and life. In the gentle depths of our cosmic exploration, where we have traced the patient journey from molecular clouds to blazing stars, there lies a beautiful truth that science teaches us. The more we discover about the universe, the more we realize how much mystery still surrounds us. The silent birth of stars, despite being one of the most fundamental processes in cosmic evolution, continues to harbor secrets that challenge our understanding and invite us to probe deeper into the elegant complexities of creation itself. There is something profoundly humbling about contemplating the gaps in our knowledge of stellar formation. After decades of observations with the most sophisticated telescopes ever built, after countless computer simulations that model the physics of gravity and gas dynamics with extraordinary precision, we find ourselves face to face with questions that remind us how much the universe still has to teach us. These mysteries don't diminish the beauty of what we have learned. Rather, they enhance it, like shadows that make a painting more dramatic and compelling. Picture, if you will, one of the most perplexing riddles In the study of stellar birth, the remarkable inefficiency of star formation itself, when astronomers first began to understand how molecular clouds collapse under their own gravity, early calculations suggested that star formation should be a highly efficient process, converting perhaps 50% or more of a cloud's gas into new stars. Yet observations reveal a striking reality. Only about 1% to 3% of the gas in a typical molecular cloud actually becomes incorporated into stars before the remaining material is dispersed back into space. This inefficiency represents one of the most fundamental, unsolved puzzles in astrophysics. Something is preventing the vast majority of gas in stellar nurseries from participating in the star formation process. But the exact nature of this cosmic regulatory mechanism remains mysterious. Is it the turbulent motions within molecular clouds that provide additional pressure support against gravitational collapse? Is it the magnetic fields threading through the gas that resist compression? Or is it the feedback from the first stars to form, which heat and disperse their birth environment before their siblings can complete their own formation? The role of turbulence in molecular clouds presents another layer of cosmic mystery that continues to challenge our understanding. Observations show that these stellar nurseries are filled with chaotic motions, currents, and eddies of gas flowing at velocities of several kilometers per second. These motions contain enough energy to disrupt star formation entirely, yet somehow they coexist with the gravitational collapse that creates new stars. The source of this turbulent energy and the mechanisms that maintain it over the millions of years required for star formation remain active areas of research. Even more mysterious is the question of how the first stars in the universe formed in an epoch when the cosmos contained only hydrogen and helium from Big Bang nucleosynthesis, without heavy elements to form dust grains, without the complex cooling mechanisms that operate in contemporary molecular clouds. How did gravity manage to overcome thermal pressure and create the first generation of stellar objects? These population 3 stars, as astronomers call them, likely had masses tens or hundreds of times greater than typical stars today, burning through their nuclear fuel in just a few million years before exploding as pair instability. Supernovas that seeded the early universe with the first heavy elements. The search for these primordial stars represents one of the holy grails of contemporary astronomy. Despite their profound importance for cosmic evolution, no confirmed population 3 star has ever been observed. They may have all lived and died billions of years ago, or some might still exist as remnants in the most metal-poor regions of the galaxy. The James Webb Space Telescope and other next-generation instruments are pushing back the observational frontier, but detecting these cosmic fossils requires observing the universe when it was less than a few hundred million years old. Dark matter, the invisible scaffolding that provides the gravitational framework for all cosmic structure, plays a crucial but poorly understood role in stellar formation. While we know that dark matter halos determine where galaxies form and how much gas they can retain, the detailed ways in which dark matter influences the collapse of individual molecular clouds remain largely mysterious. Does dark matter provide additional gravitational support for star-forming regions? Can variations in dark matter density affect the efficiency of stellar birth? These questions probe the intersection between the largest and smallest scales in cosmic structure formation. Even more enigmatic is the role of dark energy, the mysterious force driving the accelerated expansion of the universe. As space itself expands at an ever-increasing rate, what does this mean for the future of star formation? Will the expansion eventually become so rapid that it prevents molecular clouds from collapsing entirely? The timescales involved are enormous, trillions of years in the future, but the ultimate fate of stellar birth may depend on understanding this most mysterious component of the cosmic energy budget. The magnetic fields that thread through molecular clouds represent another frontier of cosmic mystery. While we can observe these fields through their effects on dust grain alignment and through their influence on gas motions, their origins and evolution remain poorly understood. How do magnetic fields form in the early universe? How do they evolve as galaxies and molecular clouds form and evolve? The interplay between magnetic fields, turbulence, and gravity in determining star formation rates involves physics that operates on scales from individual atoms to entire galaxies. The chemical evolution of the universe presents puzzles that connect stellar formation to the broader story of cosmic enrichment. While we understand the basic processes by which stars create heavy elements and return them to the interstellar medium, the detailed patterns of chemical evolution show complexities that challenge our models. Why do different regions of the galaxy show different patterns of elemental abundance? How exactly are heavy elements transported from their stellar birthplaces to the molecular clouds where new stars form? The transition from the formation of the first stars to the establishment of normal star formation processes that operate today remains shrouded in mystery. At what point in cosmic history did molecular clouds begin to look like the ones we observe in the contemporary universe? How did the gradual buildup of heavy elements change the physics of stellar birth? These questions probe the billion-year gap between the end of the cosmic dark ages and the emergence of the galaxy populations we observe today. The role of supermassive black holes in regulating star formation across cosmic time presents another puzzle that operates on galactic scales. We know that feedback from active galactic nuclei can heat gas and prevent star formation in massive galaxies. But the detailed mechanisms and timescales involved remain poorly understood. How exactly do supermassive black holes know when to turn on and shut down star formation in their host galaxies? The relationship between stellar formation and the formation of planetary systems reveals gaps in our understanding that have profound implications for astrobiology. While we can observe protoplanetary disks around young stars, the detailed processes that determine planetary system architectures remain mysterious. Why do some stars form hot Jupiters while others form systems like our own? What determines the chemical compositions of planetary atmospheres? Perhaps the most beautiful aspect of these remaining mysteries is how they remind us that science is an ongoing conversation between human curiosity and cosmic reality. Each answered question opens new avenues of inquiry. Each observation reveals new puzzles to solve. The mysteries surrounding stellar formation don't represent failures of scientific understanding. They represent opportunities for future discovery and wonder. The quantum mechanical processes that govern the behavior of matter in the extreme environments of stellar cores continue to reveal surprises. As our understanding of nuclear physics improves, we discover new reaction pathways and processes that affect how stars burn their fuel and create heavy elements. The intersection between stellar physics and fundamental particle physics promises to reveal new insights about both the smallest and largest scales of physical reality. The role of time itself in stellar formation presents philosophical as well as scientific puzzles. How do we reconcile the nearly instantaneous quantum processes that govern nuclear fusion with the millions of years required for gravitational collapse? How do the arrow of time and the increase of entropy manifest in the highly organized process of stellar birth? These questions probe the deepest connections between physics and cosmology. Tonight, as we contemplate these cosmic mysteries from our small blue planet, we participate in humanity's ongoing dialogue with the universe. The same curiosity that drives children to ask why about everything around them continues to motivate scientists to probe the deepest questions about stellar birth and cosmic evolution. In acknowledging what we don't yet know, we celebrate both the achievements of human understanding and the infinite potential for future discovery that lies ahead. The mysteries surrounding stellar formation remind us that the universe is not a completed story but an ongoing narrative of which we are both authors and characters. Each new observation, each theoretical insight, each computational simulation adds another chapter to our understanding while revealing new mysteries to explore. In the gentle darkness of space, where stars continue their patient work of nuclear alchemy, the universe continues to pose questions that will inspire future generations of cosmic explorers. In the vast, patient timescales that govern cosmic evolution, we now turn our contemplative gaze toward the distant future, where the story of stellar birth will continue to unfold across timescales that dwarf not only human history, but the entire span of time during which stars like our Sun have existed. This is a journey into deep time, where the gentle processes we have explored, molecular cloud collapse, nuclear ignition, planetary formation, will play out against the backdrop of an evolving universe that is gradually changing in ways both subtle and profound. There is something both melancholy and beautiful about contemplating the cosmic future, where the universe will become a very different place than the one we inhabit today. The Milky Way galaxy, that currently hosts hundreds of billions of stars, with active star-forming regions scattered throughout its spiral arms, is destined for transformations that will fundamentally alter the character of stellar birth. Yet, even in this distant future, the same physical laws that govern stellar formation today will continue to operate, creating new stars from the cosmic materials available to them. Picture, if you will, the Milky Way as it will exist 5 billion years from now, when our neighboring Andromeda galaxy finally completes its slow-motion collision with our own galactic home. This cosmic encounter, while dramatic on galactic scales, will likely trigger one of the most spectacular episodes of star formation in our galaxy's history. As the gravitational forces of the two galaxies distort each other's structure, vast streams of gas will be compressed and heated, creating conditions ideal for the rapid formation of new stellar nurseries across the merged system. The galactic collision will redistribute gas throughout the combined system, potentially triggering bursts of star formation that could briefly return the merged galaxy to the high star formation rates characteristic of the early universe. New massive stars will form in unprecedented numbers, their brilliant light illuminating nebulae spanning thousands of light years, while their eventual deaths as supernovas will enrich the interstellar medium with heavy elements and trigger additional waves of stellar birth. Yet this renaissance of star formation will be temporary, a brief flare of cosmic creativity before the merged galaxy, sometimes called Milkomeda by astronomers, settles into a more quiescent state as the most readily available gas is consumed or heated beyond the point where it can easily cool and collapse. Star formation rates will decline to levels even lower than those we observe today. The future galaxy will gradually transition from the active, spiral-armed structure we know today to a more elliptical configuration, dominated by older, redder stars. On even longer timescales, the expansion of the universe itself begins to influence the story of stellar formation in profound ways. Dark energy, the mysterious force driving cosmic acceleration, ensures that the universe will continue expanding at an ever-increasing rate. As space itself stretches, the average density of matter decreases, making it increasingly difficult for gravity to overcome. The cosmic expansion and gather material into the dense concentrations necessary for star formation. In perhaps 1,000,000,000,000 years, a span of time 1,000 times longer than the current age of the universe, the expansion will have diluted matter to such low densities that new molecular clouds will become increasingly rare. The raw materials for star formation will be spread so thinly through space that gravity will struggle to accumulate enough mass to trigger collapse. Star formation will not cease entirely, but it will become an increasingly rare and precious phenomenon. As the universe enters this era of declining stellar birth, the character of star formation itself will undergo subtle but important changes, with fewer massive stars forming and exploding as supernovas. The mechanisms that trigger molecular cloud collapse will become less common. Star formation will depend more heavily on galactic encounters, tidal interactions, and the gradual accumulation of matter over extremely long timescales. The types of stars that form in this distant future may also differ from those we observe today. As the most massive molecular clouds become increasingly rare, star formation may shift toward the production of smaller, lower-mass stars. These red dwarf stars, which can burn their nuclear fuel for hundreds of billions of years, will become the dominant stellar population in an aging universe where stellar longevity becomes increasingly valuable. The era of red dwarf dominance represents a fascinating phase of cosmic evolution when the universe will be populated primarily by small, cool stars that burn their hydrogen fuel with extraordinary efficiency. These stellar lighthouses will provide stable sources of energy for trillions of years, potentially offering havens for planetary systems and perhaps life long after more massive stars have exhausted their fuel and faded away. During this red dwarf era, star formation will continue, but at ever-decreasing rates. The galaxy will gradually consume its remaining gas reserves, while stellar winds and supernova explosions will continue to heat and disperse material that might otherwise participate in future episodes of stellar birth. The star formation rate will decline exponentially with each passing billion years, seeing fewer and fewer new stars join the galactic population. The role of stellar remnants White dwarfs, neutron stars, and black holes will become increasingly important in the cosmic future. These compact objects, the end products of stellar evolution, will continue to influence their environments through their gravitational fields long after the stars that created them have faded. Some white dwarf systems may experience nova explosions when they accrete material from companions, briefly outshining entire galaxies and potentially triggering new episodes of star formation in their vicinity. Brown dwarfs, the failed stars that never achieved the mass necessary to sustain nuclear fusion, will constitute an increasingly large fraction of the galactic population as the universe ages. These substellar objects, typically containing between 10 and 80 times the mass of Jupiter, represent the lower limit of the star formation process. In a future universe where gas is scarce and star formation is inefficient, brown dwarfs may become the most common outcome of gravitational collapse. The planetary systems that form around future stars will likely differ significantly from those we observe today, with lower metallicities, fewer heavy elements available. For rocky planet formation, future planetary systems may be dominated by gas giant planets and icy bodies, rather than the terrestrial worlds that characterize the inner solar system. However, the planets that do form around long-lived red dwarf stars may have billions of years to develop complex surface chemistry and potentially biology. As star formation becomes increasingly rare, each new stellar birth will represent a remarkable achievement of gravitational aggregation against the cosmic expansion. Future astronomers, if any exist, may treasure each new star formation event, as we might treasure the discovery of a rare gemstone, knowing that such events will become increasingly precious as the universe continues to age and expand. The very last stars in the universe will likely form from the final reservoirs of gas that manage to avoid being dispersed by stellar feedback or heated beyond the point of collapse. These ultimate stellar children will inherit a universe vastly different from the one that gave birth to the first stars, yet they will follow the same fundamental physics of gravitational collapse and nuclear ignition that has governed stellar birth for over 13 billion years. The end of star formation, when it finally arrives, in perhaps 10 to 100 trillion years, will mark one of the most significant transitions in cosmic history. After this point, the universe will contain only the stars that have already formed, gradually fading one by one as they exhaust their nuclear fuel. The red dwarf stars, born in the final episodes of stellar formation, will become the universe's last lighthouses, burning quietly for hundreds of trillions of years in an increasingly cold and dark cosmos. Yet even this end is not truly final, for the black holes that form from the most massive stars will continue to exist for almost incomprehensibly long periods, slowly evaporating through Hawking radiation over timescales that make the current age of the universe seem instantaneous. In the far distant future, these black holes may represent the last repositories of organized matter in an otherwise empty and expanding cosmos. Perhaps the most beautiful aspect of contemplating the future of star formation is how it connects us to the deep rhythms of cosmic evolution, the same processes that create stars today. The patient accumulation of matter by gravity, the heating and cooling of gas, the nuclear fusion that transforms hydrogen into heavier elements will continue to operate as long as the universe contains the raw materials necessary for stellar birth. The future of stellar formation reminds us that we live during a remarkable epoch in cosmic history. The universe today is old enough to have created the heavy elements necessary for rocky planets and complex chemistry, yet young enough that star formation continues at robust rates throughout galactic disks. We exist during what future cosmic historians might consider the golden age of stellar birth, when galaxies are still actively creating new stars and new possibilities for complexity and life. Tonight, as we gaze up at the star-filled sky, we see not just the products of past stellar formation, but participants in an ongoing cosmic story that will continue for timescales beyond human imagination. Each star represents a triumph of gravity over expansion, of order over entropy, of the universe's remarkable ability to create complexity and beauty from the simplest initial conditions. In contemplating the future of star formation, we celebrate both the magnificent creativity of the cosmos and our own privileged position as witnesses to its ongoing masterpiece in the quiet laboratories and engineering centers where humanity's next generation of cosmic eyes are taking shape. We find ourselves on the threshold of a new golden age of astronomical discovery. The technologies being developed today promise to revolutionize our understanding of stellar birth in ways that would seem almost magical to the astronomers who first mapped molecular clouds with primitive radio dishes or captured the first infrared glimpses of protostars hidden behind cosmic dust. These future instruments will not merely extend our current capabilities, they will open entirely new windows onto the universe, revealing aspects of stellar formation that remain invisible to even our most sophisticated contemporary telescopes. There is something deeply moving about contemplating how future technologies will transform our view of cosmic creation, just as the transition from optical to radio and infrared astronomy revealed hidden aspects of stellar nurseries. The next generation of observational tools will uncover layers of complexity and beauty in the star formation process that we can barely imagine today. These instruments represent humanity's ongoing conversation with the cosmos, our attempt to build increasingly sensitive extensions of our natural senses that can perceive phenomena occurring across vast distances and timescales. Picture, if you will, the James Webb Space Telescope's successors already being planned for the 2030s and 2040s, instruments with mirrors so large and precise that they dwarf even Webb's magnificent 6.5-meter primary. These next-generation space observatories will feature segmented mirrors spanning 15, 20, or even 30 meters in diameter, collected light-gathering power that will allow them to peer deeper into space and time than ever before. With such enormous light-collecting capabilities, these telescopes will be able to observe the formation of the very first stars in the universe, catching glimpses of population 3 stellar birth in galaxies so distant that we see them as they existed when the cosmos was less than 1 billion years old. The infrared sensitivity of these future space telescopes will reach unprecedented levels, allowing astronomers to study protoplanetary disks around forming stars with detail comparable to what we can achieve today when studying our own solar system. Individual planet-forming regions within these disks will become observable, letting us watch in real time as dust grains aggregate into planetesimals, and as planetary embryos sweep up material from their orbital zones, we will witness the birth of worlds around other stars with the same intimacy that we now reserve for studying planets in our own cosmic neighborhood. Interferometry, the technique of combining light from multiple telescopes to achieve the resolution of a much larger instrument, will undergo revolutionary advances that will transform our ability to observe stellar formation on the smallest scales. Ground-based interferometric arrays spanning entire continents will achieve millisecond resolution, allowing direct observation of the surfaces of forming protostars and the internal structure of their accretion disks. Space-based interferometers with individual telescopes separated by hundreds or thousands of kilometers will achieve angular resolution fine enough to image Earth-sized planets around nearby stars. The next generation of radio telescope arrays will dwarf even the impressive capabilities of current facilities like ALMA and the Very Large Array. The square kilometer array, already under construction, will provide collecting area and sensitivity that exceeds current radio telescopes by orders of magnitude. But even more ambitious projects are being planned. Radio telescope networks spanning multiple continents and eventually multiple worlds that will map the three-dimensional structure of molecular clouds with unprecedented detail. These radio arrays will be sensitive enough to detect individual molecular cloud cores in galaxies billions of light years away, allowing astronomers to study how star formation has evolved across cosmic time by observing stellar nurseries in the distant universe. The chemical signatures of star formation, the radio lines emitted by specific molecules, will become detectable in galaxy populations that existed when the universe was young, providing direct observations of how stellar birth differed in the early cosmos. Gravitational wave astronomy, still in its infancy, with current detectors like LIGO and Virgo, will mature into a sophisticated observational tool that can study stellar formation through entirely new physical phenomena. Third generation gravitational wave detectors, sensitive to much lower frequencies and smaller amplitude waves, may be able to detect the gravitational signatures of massive stellar core collapse, providing direct observations of the moment when protostars transition to true stars. Space-based gravitational wave observatories will open even lower frequency windows, potentially detecting the gravitational waves produced by the in-spiral of binary protostars in forming stellar systems. Neutrino astronomy will also contribute new insights into stellar formation as detector technologies become more sensitive and capable of identifying neutrinos from increasingly distant sources. Future neutrino observatories, perhaps built in deep ocean trenches or Antarctic ice, will be able to detect the neutrino signatures of nuclear fusion ignition in nearby protostars, providing direct evidence of the moment when stellar cores achieve the temperatures and densities necessary for sustained nuclear reactions. The development of adaptive optics systems for ground-based telescopes will reach new levels of sophistication, using artificial intelligence and machine learning to correct for atmospheric turbulence in real time with unprecedented precision. These systems will allow ground-based telescopes to achieve image quality that rivals or exceeds space-based instruments, while offering the flexibility and upgradability that comes with Earth-based facilities. Computational technologies will advance in parallel with observational capabilities, providing the processing power necessary to analyze the enormous data sets that future telescopes will generate. Machine learning algorithms will automatically identify and classify stellar formation regions in sky surveys containing billions of stars, while advanced simulations running on exascale computers will model stellar birth with detail sufficient to predict the observational signatures of specific formation scenarios. The integration of multi-messenger astronomy, combining electromagnetic radiation, gravitational waves, neutrinos, and potentially cosmic rays, will provide comprehensive views of stellar formation that capture all the physical processes involved in stellar birth. Future observatories will be designed from the ground up to work together with automated systems that can rapidly coordinate observations across multiple wavelengths and physical phenomena when interesting events are detected. Virtual reality and advanced visualization technologies will transform how astronomers interact with their data, allowing researchers to explore three-dimensional models of molecular clouds and stellar formation regions as if they were flying through space. These immersive environments will enable new insights into the spatial relationships and temporal evolution of stellar nurseries, helping astronomers understand complex processes that are difficult to appreciate through traditional two-dimensional images and graphs. Artificial intelligence will play increasingly important roles in both operating future telescopes and analyzing their data. AI systems will autonomously identify interesting stellar formation events and coordinate follow-up observations across multiple facilities, while machine learning algorithms will discover patterns in stellar birth data that human researchers might miss. These technologies will effectively multiply the observational power of future telescope arrays by enabling them to respond intelligently to discoveries in real time. The development of coronagraph technologies will allow direct imaging of protoplanetary disks and forming planetary systems with unprecedented contrast ratios. Future space-based coronagraphs will be able to block out the light from forming stars so effectively that the much fainter emission from their surrounding disks becomes visible, allowing detailed studies of planetary formation in action around nearby stellar nurseries. Spectroscopic capabilities will reach new levels of precision and sensitivity, allowing astronomers to measure the chemical compositions, temperatures, densities, and motions of gas in stellar formation regions with detail that approaches laboratory quality data. Future spectrographs will be able to detect trace molecular species in molecular clouds, providing insights into the complex chemistry that occurs during stellar birth and the chemical inheritance that forming stars pass on to their planetary systems. The timeline for these technological advances spans the next several decades, with some capabilities becoming available in the late 2020s and 2030s, while the most ambitious projects may not reach fruition until the 2040s or 2050s. Yet each advance builds upon previous achievements, creating a cumulative progression of observational capability that will transform our understanding of how stars form and evolve. Perhaps the most beautiful aspect of these future observational technologies is how they will democratize access to cosmic discovery. Advanced automated systems and AI-assisted analysis will make it possible for researchers around the world to participate in cutting-edge stellar formation research, while immersive visualization technologies will allow students and the general public to experience the birth of stars with unprecedented realism and detail. The data archives created by future astronomical surveys will contain information about stellar formation in billions of systems across cosmic time, providing resources for discovery that will keep astronomers busy for generations. These data sets will enable statistical studies of stellar birth that reveal universal patterns and principles governing star formation across different galactic environments and cosmic epochs. Tonight, in engineering facilities around the world, the next generation of cosmic instruments continues to take shape. Engineers and scientists work patiently to solve the technical challenges that will enable unprecedented observations of stellar birth, from the design of ultra-lightweight space mirrors to the development of quantum-limited detectors that can capture individual photons from the most distant stellar nurseries. In their laboratories and workshops, the future of astronomical discovery is being carefully constructed, one component at a time. These future technologies represent more than just improvements in our observational capabilities. They embody humanity's enduring desire to understand our place in the cosmic story. Each new instrument extends our reach into space and time, allowing us to witness events that occurred billions of years ago and to study processes that operate on scales vastly larger than our everyday experience. Through these technological marvels, we continue our species' ancient tradition of gazing upward in wonder, seeking to understand the magnificent cosmos that gave birth to stars, planets, and ultimately to us.